All right, everyone, we are live, and I am super excited about this new Wolfram physics project. If you guys don't know what's going on, I have a whole bunch of links in the description kind of talking about this new theory that he's come across and how similar it looks to some of this other stuff I was working on about a year and a half ago. And some of these similar kind of graph model simulations for visualizing what we believe could be particles or bits of particles or things that make up particles, and sort of this functional computer programming approach to the kind of puzzle. So I have my friend Sebastian Sheps on here, and I think we're in the call still. Hold up, let me see. I might have disconnected with him. He's a computer programmer and a guy who's really was familiar with and doing a lot of the John Conway stuff on the Game of Life years back. So I think we're back live. Sebastian, are you there?
I'm here.
All right. Let me hold up. Let me switch you over to that audio so people can hear you better on the stream. Go ahead and there we go. They'll be able to hear you much better now. So we're kind of digging right into this and I've been watching all the presentations on the Wolfram YouTube channel, and I've been going over and watching everything on John Conway. A lot of his stuff about the Game of Life, learning about a lot of his approaches, even reading his latest papers, especially one on a way to tile. One's on the ways to tile the 3D plane, which I think is an important part of this puzzle if we're going to create a three-dimensional space that looks like our universe, our 3D universe. So been digging into a lot of that stuff. Also been digging into a lot of stuff about sphere packing, and also Buckminster Fuller. Even some of the stuff on sacred geometry, Metatron's cube, the Platonic solids, and all the weird stuff and synchronicities of geometry. And also I've even been digging into some of the more advanced, some of the Brett Weinstein stuff on these hypergeometries and his geometric unity theory, because I think that's also quite interesting and might have a lot to do with this puzzle or this generating function. So what I went ahead and did is I went and downloaded a free trial a couple days ago. I got the free trial of Mathematica, Wolfram Mathematica, and I encourage everybody who's interested in watching to do this while you're home on quarantine. Yeah, it's a 14-day quarantine, and luckily the trial period is 14 days, so it works out quite perfectly for all you guys stuck home with nothing to do, bored out of your minds, who want to be part of something really cool and interesting. Yeah, so we downloaded this software, and these are some of the files that we have up on our cloud right now. And I kind of want to set up an area where people can work on some of this stuff and share their work, and we can kind of create a collaborative network of people programming different types of functions and experimenting with the. So I gotta find where the I gotta find out where these files were, because I had.
Which ones are you looking for? Maybe I can help to pull up some of them.
So they were on the cloud right here. So this was unnamed right here. This one, okay, right here. So so we get this one that we had started working on, trying to come up with this programming function for creating nodes and networks and creating a grid-like graph, ways to tile the plane basically, and why don't we go over some of these functions, and you can I'll let you do a share screen, and you can kind of show people give us a
Absolutely.
tutorial, because you kind of got a lot of this working and helped me with this. You have a lot more experience with this kind of stuff than me, so I'm gonna let you.
Absolutely. Cool. So thanks, Jeremy. So yeah, my name is Sebastian Chepis, and I love this kind of stuff. I'm not going to get into a personal intro here. I'm just going to jump right in and talk a little bit about the Wolfram model as described by Stephen Wolfram and kind of what's happening here. Essentially, what we're looking at is a very simple substitution model. So think of like a set of elements presented before you, and then arbitrarily maybe pick a subset of those elements, and then from that subset, kind of define a third set that you're gonna use as a replacement. And then if you start out with that initial set and search for any subsets that are of your fine set and replace that with that larger replacement set that you've got, and you keep doing this iteratively, what happens is you start out with fairly simple initial conditions that can very quickly start to blow up in complexity and start to show behavior and things that you may not have ever, that you certainly would not expect from a very simple function, right? So what we're looking at right now, for example, on my screen, is an evolution of a very simple system that progresses rather quickly into a fairly kind of elaborate, multi-branched type of system that we see here. And really all we're doing to create this complexity is we're starting out with a single element that's looped back onto itself. And then from that single element looped back on itself, we run a replacement function until this complexity grows like this. So from one element, we look for individually looped elements, and we replace those with basically element pairs that have got connections to themselves. And we just repeat that process over and over again until what you see here emerges. So like if we look at the rules to do this, the rules are fairly simple, right? So here we have our font. Our font defines a single node, right? And that node is connected to itself. So when you see a pair of numbers like this, the number refers to the node name or node identifier, and then the second element refers to the node in which it's connected to. So here we have a node that's connected to itself, and we have a replacement for it. So what this means is that for any time I find 0, 0 in our graph, I'm going to replace it with 0, 0, 0, 1, 1, 1. And I run the Wolfram model method to do that. And basically all it is for you developers out there, is it's a recursive search and replace, right? And you just do it over and over again. And here we're plotting out the results of that. So from a single node, we get all this, right? So you can see how complexity can quickly blow up and start to exhibit behaviors which you never thought were possible, and also structures which you would never see if you just looked at the initial starting conditions, right? And if we look at another one here, for example, we start out with two doubly connected, two nodes. One, each is connected to itself and the other. And with that, whenever I find one of these, I replace it with 3 nodes. And again, we see complexity arise very, very quickly in ways that you never really would have imagined initially. And that's kind of the fundamental premise of what Stephen Wolfram is talking about here, is essentially from simple systems with initial starting conditions and a simple set of rules, you can very quickly generate systems that have tremendous complexity, and also something called computational irreducibility, which means that you can't actually know what the state is in the future unless you actually do all the work to get there. And that's a fundamental property of a lot of these systems that we're exploring here. So that's kind of the basic intro to it, and the methods to use to do this are really simple. And we'll make a template available for you guys that you guys can just grab and use and play around with. But here's the basics. You start out with your initial conditions here, and you make it go. I have it set up so that it'll just plot for the first 10 generations.
So
yeah,
I have a question. How do we, so go back to this model at the top, and 0 is connected to itself once. What if we were to change that and make 0 connected to itself 3 times?
All right, let's do that and see what happens. right? We're gonna.
This is what I like to do, is just play with. Yeah, there you go. So that's how we do that. Just add it in 3 times.
Right. So here, like we've got this starting set of conditions, and then we're going to rerun everything, and it takes a few seconds to execute all this stuff.
I don't know if I can
And here we
blow it
go.
up any bigger.
Oh, something is. It doesn't like something about that particular call. That's interesting. So there are some places here where it causes problems. It may be due to another statement I had ahead of later, but let me take a look too. I may have gotten it wrong. But do I have commas in between all the elements? Yep. So I'm not sure what happened. Let's try with like a doubly connected set.
Try to do like 4 steps instead of 10. Or, you know.
Absolutely.
So that comma there is the number of steps. So people get this.
Right. Exactly.
How to play around with it. This is a good introduction, because this is stuff that I would do, as a programmer, to learn a new language or learn a new programming method. Is just to kind of copy and paste what other people have and play around with it. So it'd be good if we can get some files up on the cloud with different ideas, and then we'll start working through different models and different ideas and plotting them and seeing how they work out graphically, and just get a project going. This is the physics project that I think I think Stephen was asking people, or hoping people would get out there and engage in, people of all different math levels and interest levels.
Absolutely. We can also take a look at some of the other stuff that we were playing around with yesterday that defines some interesting, that kind of multicolored hypergraph, and maybe talk about kind of what the basics of a hypergraph is and what that might mean.
Yeah, also the difference between branchial space and the hypergraphs, and sort of that whole graphic that's on the main page of introducing the whole theory. That's a good. That's a bit confusing, and
absolutely. So you want me to? I can talk a little bit about that as well. So I'm sure most of you guys have seen something called Conway's game of life, right? Conway's game of life is a cellular automata. A cellular automata is basically a grid of cells, each of which either has an on state or an off state. And that grid of cells is going to evolve over a set of iterations, right? Those iterations are called, we're going to call that time here in this particular case. And so we may start with a random state of some on elements and some off elements, and then we're just going to iterate through all of that, and we're going to change the state every single time of that element. And in doing so, we essentially we start to animate a behavior which, from the perspective of the algorithm that you're running, really don't look like much. You're just turning cells on and off, right? So, but if you change your perspective and you look above the automata and you look down at it, you see things that remind you of other things. Gliders that move, oscillating elements that will oscillate back and forth in time. You start to see this behavior that really doesn't, you can't see from within the algorithm, if you will, but when you're looking from another perspective, you can start to see that something that looks like something you would have never expected. Again, emergent behavior is what that's called. I think the same thing is going on here in Wolfram's idea of branchial space, and also real space and real time and all the other fundamental forces. So you have a graph that's evolving over time, a set of points with connections that are growing and reconnecting themselves. And when you look at that set of connections from a different perspective, you can start to see this phenomena emerge. And so branchial space or branchial time is all about how the graph evolves. So each step, each iteration, each time you process the whole thing would be like one step forward in time. And basically the model is run over and over again in time. That branchial time shows the evolution of the model. It's not exactly equivalent to real time, because the purpose here, the goal, is to build these basic structures that essentially show the show all the constants and the behavior that we know from our standard model emerged from these much simpler types of rules that are put in place.
Right, but some of the other things that I wanted to point out that I kind of noticed that was the issue of if you have these things that are particles, right, and they're sort of behaving the way that, according to the laws of quantum mechanics, then you have things that are going forwards and backwards in time, and you kind of have all these possible states that and you take like you sum over the path integral of all of them, and you get like this the most probable one, and that's sort of what you solve for, and then there's that renormalization theory and everything to kind of account for the infinities and that process of doing it, but that's kind of not what nature maybe does, but nature does this sort of selection game according to quantum mechanics, and I think that part of that needs to be part of the puzzle of things going backwards and forwards in time, and then outlaying these essential probabilities that can land on one of these things, but also the fact that a lot of these probabilities are 50-50 and can be affected through essentially what I call conscious thought. Because we make decisions to basically break down the wave function at every point in our life to kind of, there has to be some sort of, we're not just cellular automata, we're conscious beings. I would like to think that, we're not just going according to some function, that we have free will. Um,
Absolutely.
so
I mean,
that's
interestingly enough, a lot of this stuff refers right back to some of our oldest philosophical teachings that we have here on this planet, talking about how one consciousness multiplies into a myriad forms. A lot of these mythologies even contain a lot of this, a lot of similes, which you'll find in a lot of the stuff that you're exploring. So here we may end up with a grid that essentially has kind of a self-similar reflections of the entire grid system in a single point in a way, which fundamentally corresponds to something called Indra's net, which is something in Hinduism that talks about the net of existence, where every pearl reflects every other in the universe. And so we have these concepts that are that are similes. So it's an interesting exploration, because what is old is new again, right? So pretty wild stuff.
all right. I just want to give everyone the spelling of that because it's Indra, Indra's net, and it's this whole it's the idea of a shard world, like that we're all like part of like a crystal that was once the world, and it shattered into a million other crystals that reflect symmetries of the original world, and all the little crystals. Or dewdrops on a spider's web, that each one's a universe or a sphere inside of the universe, and that each point in the sort of each point in the universe, or each particulate of matter, sort of creates an inner and outer reflection of the entire universe, or at least its local um, universe around it.
Yeah.
Um, and also wanted to point out that there seems to be something, spin is definitely a big part of the model, and understanding what spin looks like, um, because we have the universe is just, I just can't help but point out, I had it over here on the other screen, the pictures of this was before Indra's net. That's right here. So before Indra's net, I was looking up how atoms are basically electrons that are circulating, or rotating in a manner, kind of an electron cloud. This is kind of the Bohr model. It's not really the most accurate depiction, but solar systems and galaxies would probably be a better, that there's all this stardust and stars, trillions of stars rotating around a galactic central point or black hole, and that inside each one of these stars is a supermassive gravity well, which has a bunch of planets rotating around it, which one of us is obviously the one we're living on. So it's kind of this whole repeated kind of symmetry. The symmetries like this emerge in systems of complexity, and I was looking up things in math to try to understand this, and one of them I came across was the Tracy-Whittem distribution, where it talks about a crossover function between two phases of weakly versus strongly coupled components in a system. So there might be these components in this system that, as you iterate this function out and create this space time out for longer periods of time, that you get these sort of these coupled components that come together at these scales. One being the smallest is the atomic scale. That's basically what it's built of, and then the fact that kind of comes out at the solar system scale and the galactic scale again for galaxies. I think that's an interesting piece of the puzzle that I've rumored on as well. E8 still valid in 2020. Oh, so how does E8 fit into this puzzle, and what is that? What is sort of this? So this is kind of the way we think about these geometries and active and mirrors. It's sort of like it's great that they have this it's a mirror point. And that this describes pretty much all the geometries according to these Dinkin and Coxeter and Dinkin diagrams. And the E8 is what's called a Lie group, and this is all part of group theory and a lot of number theory and stuff, which is like, this is why it's the core of mathematics, and why this this sort of Wolfram physics project, I believe, is crucial. It's going to be key because it's going to unify physics and math into one, and show why Garrett Lisi shows all those E8 symmetries groups where all these similar rotations of the of that. It's basically a shape in these higher dimensions, and that when you rotate it in around certain axes, it has these interactions that look just like particle physics, and we say, oh, like parts of particle physics could relate to this somehow. So they knew it has something to do with group theory, but there's things that go on inside E8 that aren't really predicted or aren't really seen in particle physics, that aren't really part of the whole particle puzzle. So they kind of dropped that and tried to find another approach. That other Gravity Research Foundation was working on that whole approach, where they tried to basically overmap. They tried to select out the parts of the E8 theory that worked and eliminate the parts that didn't fit the model by drawing a quasi-crystal over the E8 group. And saying that the points of intersection of this quasi-crystal with the E8 group was like the theory of everything. But that turned out to have problems as well. Geometric unity, yes. I think what we're doing, what is being done, I don't know if we're going to be the ones to do it, if we really have the level of understanding to really put this all together. But it would be awesome to basically find this generating source code that could create all these geometries. And one of the things I was looking at for a potential is some of the unsolved problems in physics and math, which might just be related to this. And one of those that I came across, of course, one of the most famous and oldest, most long-standing, is Fermat's last theorem, which is, of course, one version of n equals 2 is Pythagorean's theorem, right? But this kind of extends Pythagorean theorem to all the other n greater than 2 dimensions, integer dimensions. So very interesting number theory, part of number theory, and it might just be a good clue to an axiom for our generating function, to say, obviously it's never been proven that this is true, but just why don't we hold that true and make it true for our generating function, and then make that, you know what I mean?
Yeah, absolutely. In fact, I have a sneaking suspicion that in a lot of places here, we can actually just essentially start looking at the set of all possible solutions for a particular problem, and start looking at the one at the ones that are essentially the most elegant, right? Just like everything seeks its lowest energy state, in classical physics. I do believe that what we'll find here is that also the design is going to seek as simple as a state as it can be in order to do what it needs to do. Nature tends to do everything perfectly, and as such, I very much expect that reflected in what we see here. So,
So this is
yeah.
this is again back to these Coxeter-Dinkin diagrams and how they relate to the Lie groups. That whole E8 puzzle. So E8's just one of these Lie groups on this whole chart. There's this D4, there's D8, there's this B8. You know, I don't know what happened to C, but there's all these. Maybe C is complex. That's why it's not here, because these are all simple Lie groups. They didn't want to have C for a simple Lie group because it's could be confused with complex. That's probably why there's no C. But in any case, these are all different, basic Lie groups. But the way that this works is that there's a symmetry, and then it's connected out to another axis. And if you create more and more of these points, and then rotate them around this central like symmetric point, is kind of how these shapes are created. And it goes. This was all deduced from studying polyhedra, polygons, like going way deep on Metatron's cube and all all that sacred geometry. Like people want to talk about sacred geometry, like that's like it's really interesting stuff, and this was known to the ancients, which makes it even more interesting because there's things like Indra's web, and Indra's net, where it's comes from scripture. It came from scripture of like the ancients kind of have this whole inkling to, this kind of stuff too. Maybe they had, um, maybe they had advanced knowledge of this or not. That's a whole nother story. But again, this takes like basically studying all that stuff with Buckminster Fuller and that's like the basic introduction to it. But it takes studying all these shapes and the symmetry groups to this whole other level. This is like
Right. And sometimes and often all of this complexity just springs from very even simple philosophical concepts. So let's consider the case where there's a single something in a hypothetical universe. That single something appears, and then to perceive itself, it needs to bifurcate somehow or another. So it's going to do so, but it still is itself. So it's going to seek to be as much itself as possible, and also as separate as possible. It's going to seek balance between those two states, and you can represent that with essentially a circle that splits off into two, but only moves a radius apart in order to essentially overlap itself. Right? It's both two and one at the same time at that point. So you started the first process of actually drawing out the flower of life when you make that movement. And essentially, that's what it's all about. A simple philosophical concept that is then iterated recursively until that complexity emerges and proves itself.
right. But according to this, it might take you know several thousand iterations just to create something. In with this kind of a model. One example is I wanted to kind of show visually for that was that large Buckminster, the biodome there, and kind of this whole idea of this massive sphere. Yeah, like this, right? So the proton at the middle of this that just links to this whole geometry network of empty space out to this event horizon where is the lowest energy state where the electron sits. And how that all fits together in a puzzle with geometry and just as a bunch of connected points in space. So back to that, some of these interesting models that he had and was working with. I wanted to try to play around with some more models and do some more stuff. So have you seen this one right here?
Oh, that's a good one.
It's got the squares, and it basically it creates these bubbles on the squares. Now I was thinking of something like this, and kind of something similar to. He had these drawings of how general relativity would work, and as a sort of like that. This grid or this interconnection of structures, which is space. And if you measure the distance of things, the measuring the distance is actually measuring these structures between things, and you can do that by shining light of different frequencies, which will get there in a certain amount of wavelengths.
Interesting. So this particular grid represents essentially physical space with like some interactions happening between these.
Well, this not grid, not the one we're looking at right now, but the one we're trying to build.
Yeah, yeah.
Right. If we want to build something this physics model, right?
Right. Absolutely.
Um,
And yeah,
what I was
this,
let me finish the thought real quick though. Is the whole idea is that taking points out of the grid, by separating them out, the space bends around to fill in the gap of where you took something out. So this might be a way that we could, have gravity work in our model.
absolutely.
But this was interesting nonetheless. To try to, I wanted to maybe play around with this and see what it did. It does some interesting things over time.
Do we? Is there a script available for that one? It says copy to clipboard. I would imagine there may be an actual Mathematica script we can play around with. Interesting. Just click on it and try to paste it into a Mathematica notebook, and that may be all you need to do. That's kind of what I've seen in terms of how they structure their stuff. Just click on an example and paste it in and run. But yeah, let me see where that's at.
How do I run this now?
Do you have a Mathematica open, like online? Yeah, paste it into your new notebook.
Yeah, I pasted it into the notebook here. Is it? I might have to change the.
And then just do Shift Enter to actually run the thing right on the last line of the code, and that should run it.
All right, so it sped out some model. Okay. I think I gotta take out these parentheses. Oh.
Yeah.
It put parentheses in there when I copied it,
Yeah. Sometimes it's a little weird when you first paste it in, but just essentially it's usually you just paste it and Shift Enter to run the thing. I wonder if this one just creates your output set, or does the actual plotting.
All right, so it's looking for this graphed object that I have to get as part of this other. Let me find where that was. No, I lost it. I got too many windows open.
If you want to send me the link via message too, I can work on it from my end as well.
Right. Yeah, I just want to play with as a couple more of these. And do you want to go over some of the other examples that you did, and I'll let you take the.
Yeah, totally. Like I'd love to talk a little bit.
Oh crap! I closed this window.
And essentially, what we're doing here.
Hey, sorry about that. Can you just? I closed your window on accident, so start over.
Oh, no worries. Okay, so so I'm going to take you guys through a quick little run through of some of the stuff that we were doing last night, playing around with the capabilities of Mathematica as well as exploring hypergraphs. Right. So what we're looking at here is a function that I found online for actually plotting a neat looking hyperplot that comes with pretty colors and nice labeling, which is cool. You can do a lot with this program in terms of how to visualize this stuff, which is key in being able to understand and have good ideas and intuition and stuff like that, and how to progress. In any case, what we're looking at here is a simple hyperplot. Well, actually a fairly complex hyperplot where we've got 7 points that are hyper connected to each other. And what we were exploring here was kind of the start of Metatron's cube, I believe, right, Jeremy? I think this
Yeah,
was
sure. Why? Yep. I said, why not? Let's try to build the Metatron cube kind of idea. It's just
yeah,
where
and if
these points would then be mirrors in order to build it up, build the entire grid. You
absolutely,
just
and the thing
iterate a step out and then a step out, and it would just build this flower. This flower would kind of go outward and build this whole symmetric universe. And then I kind of had this idea of this vision in my head about a hollow mirror sphere, a sphere that's just mirror on the inside, so it reflects. You gone in an elevator. I've been in with those elevators that have mirrors all on the inside, and they kind of reflect. It makes the reflection on each side gives it the illusion of infinity. And
Yep.
I always thought that hey, if we you have this illusion of infinity, but there's this ever so slightness, the mirrors can't ever be perfectly aligned, so there's always going to be a
Absolutely.
slight curvature to that, over time, and that curvature,
Absolutely.
there's a point that vanishes from where
Absolutely.
it's vanished and it's no longer connected to visually, the original point of the system, and then you get a symmetry breaking where all these spheres aren't exactly the same. There's two that can be a little bit different because they're around that hypercurve,
Right.
in hyperspace, and so I
Yep.
kind of
And the whole system has inherent periodicity built into it from the start, because if you look at kind of how how those reflections occur, the initial seed, if you will, has an end, right? Has some type of value, and as you're reflecting that value over and over onto itself, you're creating multiples and harmonics of that particular initial value. And you have multiple harmonics that are growing out into space and that are going to converge it in particular points, just like you were talking about earlier, Jeremy, where you have a function that shows the strong and the weak interaction, and you have very distinct phase transitions there, which transition over from kind of one behavior that is fundamental to another. And these transitions happen very quickly and suddenly, even though each of the processes might be very like their expression might be very smooth in terms of like how they express over time or over space. I think the same thing is happening here. Like, again, the Planck length is likely one of those fundamental types of things that's built into all of this, or maybe the Planck length is the very thing that emanates from the very fundamental activity that happens. And then once there's one, there is many. Who knows? But it seems that way. These systems certainly point in that direction. And it has to be that way. It can't be some weird, crazy, stupid, arbitrary thing. I mean, maybe it can be, but I tend to think it's not. I tend to think that we're going to see elegance, because that's the way things are fundamentally. So it's an exciting exploration that like everybody should be part of, because you don't need to be a physics genius to do this, to explore some of these concepts. You can just get started.
All right, so I'm gonna watch this real quick.
I've always wanted to be a teacher. With everything going on, we've had...
I want to see this video someone suggested about Vsauce inside of a spherical mirror. I guess this guy, maybe did it. Did he do the experiment?
Oh, that would be interesting.
You'd have to build a huge one.
But you are actually.
Well, I mean, essentially,
right
we
there.
can sort of do that with we can
camera
do
is
it mathematically here with Mathematica and kind of reflect structure.
I want to see what it looks like. So he's doing the two mirrors
with Star Wars. And my
So
friend
he
Russ
actually did this.
states the potential for.
I don't think he actually did the experiment.
It would
He just
seem-
talks about it. All right, so you got to do the experiment. Someone's got to do it now.
Totally. I mean, you don't even need to do it for real. Like, you could use ray tracing and rendering to kind of to at least show you what that would look like mathematically, right? a ray tracing application essentially reproduces what we understand about how light rays work, at least close enough that it's you can make stuff that is identical looking to what you would be expecting. So that's a way to do it. Like if there's any people out there that know how to do computer modeling, computer graphics, do a ray traced self-reflection of the inside of a sphere and see what happens. It would be fascinating to see.
Right. Yeah, I can't wait. I'm going to mess around with this program for the next 12 days that I have left of my trial version. I think if we start getting somewhere and we get enough people on here collaborating, then I'm definitely going to buy this software and start,
We're definitely buying it. There's no doubt about it. This is just the start. I think that we can definitely get somewhere pretty freaking awesome. I mean,
yeah, the universe is a fractal. People are talking about fractals. This is definitely, it's fractal. So let's talk about the Mandelbrot set and fractals for a little bit. So before that, they had computers. This guy discovered the Mandelbrot set. And he did it just by this simple recursion relationship. And it's, we take the function of z and you plug z in, you square it, and you add c.
Yep.
And as long as z is below below 1, right, is less than 1, because if it starts getting greater than 1, then you square it, it starts blowing up huge and goes exponential. But if it's less than 1, and sort of this Goldilocks zone between 0 and 1,
Yep. And then all of a sudden you have this.
It starts jumping around and never quite lands on a point, but it creates this whole thing, and he noticed it because it created this set function that kind of went random, and he just did it out to like thousands of iterations, and it just looked like, it probably looked like this, the drawing, and then there's this correspondence of this bifurcation in the map. It shows the chaos points where there's these simple parts. Really, it goes really simple, then it bifurcates. This is this doubling,
Yeah.
This is called bifurcation, and then it creates this chaotic point, and then there's these little points of stability at these little points in it. And anyone who's ever, I used to have math programs on the old computers where you're able to zoom in, and it would take like a couple hours of rendering sometimes to zoom really far in, because they would have to calculate it all. But I had this program that you could zoom into the Mandelbrot set and Fractal Explorer program on. I forget what it was, but it was.
It was awesome, man. I don't remember the name of it, but I had a PC XT when I was in high school, and that thing weighed about 100 pounds, and it went so slow, but it would chug these out. Sometimes it would take a whole night to create a really detailed Mandelbrot set, but it would do it.
All right, that shows the bifurcation. This is a much better visualization of how that works. And
it's such an awesome set. If you look at if you look at the kind of the vertical dimension of it, and how the Z changes in that, there you go. That is so freaking cool.
I know, it's like super cool. It looks like a Venus flytrap.
Yeah. It's like you think that you think you've seen it all, and all of a sudden you shift your perspective on it a little bit, and there's this whole new world that's revealed from your perspective. And I think ultimately that's key for us understanding this is essentially these graphs are generated, and then we have to look.
Our reality is just a projection on the 3D space of all this other shit going on in hyperspace.
Right. Exactly. So interpreting what we generate will essentially mean looking at it from a particular perspective, whatever that is, a mathematical one or a visual one, or a one that we select as we render this data. That's how you find the emergent behavior that you're looking for. At least that's my intuition. Intuition says here.
This is so key for explaining that too. It's like what we just look at is that top down, that one, just looking down the z-axis. But then when you start looking at it from this angle, it just opens up this whole nother realm of dimensionality to the puzzle. And that's kind of like what we need to keep in mind with what's going on with this other theory, is that we live in this three-dimensional universe, which I think kind of makes sense from the way Ken explained his theory, how he got all particle physics to work through this sort of Phoenix theory model. And maybe that would be a good model, a good place to start for a model as well. So the way that the Phoenix theory pieces would work, and we've been trying a little bit to engineer these too. That was kind of the basis for that flower of life model, where you have 6 things coming out, because the connections can be positive or negative. That's a key part of this, is that that these negative and positive connections go forwards or backwards in time. There's a direction or an arrow of time in all these as functions. And I don't understand all of it yet, and why why the arrows go all these ways in the models here. But according to this theory, the electrons that single point 0, 0, 0, 0, 0, 0, 0, 0, connected 3 times, like you had said. So that would be an interesting place to start. And one of the ways that he kind of built this thing out in 2-dimensional space is a series of 10 triangles. Well, there's 10 of these different possibilities, permutations of these three different possible connections on a single vertex. So a vertex in 3D space is connected in 3. So all the things that should matter or function in our 3D universe should have this kind of 3 connectivity. So that makes sense. And
that does make sense, and that kind of, you see that everywhere too, like in all kinds of sacred geometry. That 2 and 3 is really fundamental. Like if you look, for example, if you look at numbers that are multiples of 2 and 3, so multiples that break down to 2 and 3 as their factorials. The digits in those numbers will always add up to 9 no matter what. It's just a feature of those numbers that come from those particular factorials, right? And a lot of people will dismiss that as numerology, but it's not. It's not. We're reducing a number to its core, and because we're dealing with systems that have periodicity and reflections that occur on higher scale harmonics, you can look at a smaller part of the system and kind of understand the greater aspect of it as well, which is crazy because it relates back to the most ancient things that like philosophy used to say about as above, so below. That's exactly what that means. It means what is greater than is the same as what is less than. What is bigger is the same as smaller. Everything scales in both directions, and that's a fundamental property of the universe, and it's bound to be everywhere.
Cool, man. This is interesting. So this is kind of one of the ideas I had to start. But what if we could just create where the whole lattice is? Because if you create this and you expand it out, that just creates that hexagon grid lattice.
Absolutely. Like there's a couple of things I want to play with. There's the basic. There's the kind of the basic graphs that we are looking at here, whereas essentially what you're dealing with is a process of replacement, where you're essentially growing that graph, and from the pattern of growth, emergent behavior, which is cool, and I want to look at that because I do believe we'll find some interesting stuff there. But the other thing I want to play with is what we were talking about yesterday with essentially using a flower of life grid, which is nothing but like a doubly connected a hexagonal grid and then from that essentially create maybe play around with different types of cellular automata state machines. So like imagine the point that I'm looking at right now, like where you have where I've got a hexagonal grid essentially that has a center point. It's easy to create a system where essentially a set of rules act upon kind of the polarity of each of these points. So like you could say for each central point or for each point in the system, if there are 3 positive points emanating from it, then transform it into their opposites, right? So essentially, you would be flipping these bits, if you will, at this level, and then you just do that recursively over and over again and see what emerges at a higher level. And I have a suspicion that this particular type of grid will be very interesting to play with because it's just so damn cool, and because so much can fit on it. The way its geometry allows for all the platonic solids to essentially kind of find like a nice low energy fit in the grid itself. Like if I was going to tile anything, if I was going to tile reality, it would be this way because it's so efficient. And so this is kind of the way that I think is worthwhile playing around with. And so I think we're going to take a couple of approaches to it. Is play around with some of these kind of what Wolfram is doing directly with growing these grids, and also play around with possibilities on essentially these kind of reality grids and see what type of phenomena we can generate here. So.
Right, everything in the 3 dimensions, and try to explore in that area with sometimes. But there's also things that are connected in different ways with different types of geometries. But is that a hypergeometry manifestation of a much simpler,
Right. Like
building block?
Is like 3 dimensions it, or is there a larger like dimensional reflection? I don't know, but it seems to me as though 3 dimensions perfectly maps down to 2 here, especially on this grid, which essentially, if you look at it one way, looks like a 3-dimensional grid, and if you look at it another way, it looks like a hexagonal 2-dimensional grid. Again, there's a strong relation between those numbers, and so 2/3, I think, is going to be. It's one of those seed ratios that will then blow up into all kinds of different, permutations and interesting harmonics of itself, right? And so that's what there's to play around with. Now I have to teach myself about 5 years worth of math in 3 months, which is fine. It's worth it for this. Like, this is where the secrets of the universe are. I'm convinced.
Yes. So the next step, of course, the first step is to create a proton and with an electron orbit in it, so we can create hydrogen, and then to get all the and basically get all the spectral emissions for hydrogen. If we can do that, we'll have gotten a real far first step in the physics process of the theory. But then after hydrogen, we need to, of course, come up with a plan for how we're going to create all the other elements. And I was looking through some of this, and one of the numbers that always comes up, and Feynman said that physicists write this number on their chalkboard or on their whiteboard and worry about it, and it's the number 137. And 1 over 137 is this fine structure constant. It's almost exactly 1 over 137. I think it is, like, to the degree that they measured it, they think it's almost exactly 1 over 137. And it appears in a lot of these equations in quantum mechanics. And another thing I was reading up on 137 I thought was interesting is that it says that in the Bohr model, the innermost electron of an atom with z equals 137 would be orbiting just below the speed of light, and the next element, z equals 138, would be impossible because it would be going faster than the speed of light. Right? So since the Bohr model doesn't include either quantum mechanics or special relativity, that fact that it breaks down in this regime is not unexpected. However, such large atoms, if their nuclei were stable, could be expected to behave rather differently from a naive extrapolations of trends in the periodic table. But again, it's kind of interesting that there is a limit to the periodic table of elements. That I joked on Twitter when I found this earlier that Bob Lazar should have picked element 138 instead of 115. But
so I wonder if the fact that 137 is a prime has anything to do with the fine structure constant. Like, this is.
I wonder what that number is, and if it has to. I'm thinking it has to do with some sort of facets of the geometry that are filled, and so there's got to be some kind of model for the atoms and
Right.
And also the shapes of them. Very interesting. Carbon diamond has the tetrahedral symmetry, and of course it has the 4 valence electrons in the Lewis structure. So it bonds very similar to a tetrahedron.
And here's some interesting thoughts, right? So I can think right away of like on that hexagonal grid, a way to essentially create a structure that is going to oscillate. And that
There's a
structure
couple
may
people have done this already.
yeah, I mean, like for sure. But like an
Find the
oscillating
other.
structure, right? Like if you have an oscillating structure that essentially has termination points where it oscillates and it reverses its oscillation, that defines a physical bound, right? So like my intuition says, look for oscillating structures that essentially resonate out to a particular length on this grid, right? Maybe take this grid and define it so that each one of these lengths is my brain is shot right now, but the what's the smallest possible length? I cannot believe I don't remember this right now, but you know what I'm talking about.
Yeah, the Planck length.
There you go.
Yeah.
Like make each one of these lengths the Planck length. We know some of these, what the Planck lengths are for some of these elements. We know, so we have we have targets that we can look for already, right? And I think it's going to be like pairs of resonating structures that define these kind of boundary conditions at different lengths in this structure, right? So that's, I don't know, that's my intuition in terms of what I have seen in my own personal explorations with cellular automata where I see these kinds of structures that start to emerge from oscillations, if you will, right? Because if you look at something, say you're looking at a multiple frames of a thing, like if you're watching a movie, the balloon may be, kind of like, or the thing may be in one place in one moment, and another place in the other, and it looks like it's bigger just because it's vibrating so fast. So maybe size itself isn't, maybe the proton actually isn't that big. It just seems like it's that big because it's vibrating in a way where its kind of boundaries, where it's reflecting back into itself, is that at that length. And for some reason, there's something to do with a prime there. I don't know why, but there's probably a good reason for that.
Right. So I was trying to get I want to do some of the other things. I still got to learn a little bit better how to do these vector plots and other things. Let me see if it's.
You were, Jeremy, you were talking earlier about like perhaps like kind of creating a place where like people could come and talk about this stuff. It might, if people are interested, maybe we could consider building. I could definitely create a chat space somewhere where we can all get together and kind of post ideas and stuff like that. I think it's certainly worth having a collaborative space to do it. I'd be happy to take that on and make that happen for everybody if you thought that was a good idea.
Yeah, that would be cool if we could set that up too. And anyone that's interested in joining can email me or actually Twitter would probably be a good spot to get in touch with me, or here on Facebook, leaving a comment. But I'd like to get a couple people involved in sort of playing with these models and seeing what we can come up with, because this is really neat stuff. I want to talk about a couple things from some of these working sessions that Wolfram did, because I watched all of these, and I wanted to talk about a couple things that were brought up. One was he was talking about black holes, and it was also talking about angular momentum, what's spin, what's angular momentum, and what's charge, and how do we model that within, how would you model that within, this sort of branchial space. Very interesting the way that they ended up doing it or are talking about it, but it was basically these arrows of time for these connected points kind of go in a vortex around a central point, and that they kind of sum up to make things that actually go in this and can build rotations. And then he was talking about in this kind of hypergraph space, the creating another chain, and this was kind of like this area in the middle represented a black hole, and this was just one side of the black hole. This would be like kind of every side of the black hole. This would be information dropping into the black hole, and then it goes into the black hole and it doesn't ever get out or affect information or logic chains outside the black hole. It kind of gets sucked in. And in the process of talking about this, someone asked him about, well, what about wormholes? And and he didn't really answer the question in any give really a good answer, but I thought it was cool that he had talked about in another one of these the idea of quantum computers. I don't know if it was this one. I think it was a different. It might have been this one
Continue
right
having
here.
branch pairs and track.
And no, it might have been in a different one. But he was talking about basically where a quantum computer is in these branch pair trains, and
Actually, we don't probably want -3.
how a quantum computer is basically like breaks off the same way as a black hole. It looks like the same way as a black hole breaks off from this sort of the rest of the information network. And this is sort of what Ken and I were talking about with the way to create a warp drive, which again I got
Right,
people gotta ask people keep asking me about the warp drives and what's going on with the warp drive. But yes, this theory does technically allow for warp drives, because it's basically if you break off these information loops and create a black hole around your craft basically the way you'd have to do that is turn the skin of your craft into a quantum computer, which is right in line with what Jack Sarfati has been talking about. I know he was mentioned in the comments. Yes, you could create a warp drive with a quantum computer, wrapping a quantum computer around your craft,
Yep.
but how to build that and how to do that is another story. But and whether that's a lot more complex than some of the other methods or ways that we might learn for creating propulsion, or other ways to manipulate space, time, and fields, and with our better understanding from these new models.
I think it's
Who's to
possible.
say? Who's to
I
say?
think,
But it's possible. The fact that it's possible is really cool.
yeah, for sure. And I mean, we're already entangling macro systems with using our knowledge of quantum physics, and we don't even know how quantum physics works, right? And we're able to already create entangled systems that exist at the macro level. Like, imagine being able to entangle much larger system, as a spaceship's worth. Right away, if you can slip right out of the causal causal stream of this particular manifestation, you can essentially you essentially have yourself a warp drive, and you're essentially completely independent from any causal ramifications of anything that occurs in this universe. Like, you could
how do you like reconnect back to the past? Like, how do you get back from this? Like, at some future date, you gotta like go down the logic chain and reconnect yourself back in with the networks.
Right.
And
Somehow or another.
how does that work?
You have to find I would imagine that you have to find a condition in this particular real space where that allows for essentially a valid kind of flow of information, right? The system is constantly transforming. It's constantly changing, which it is. It's like the system is constantly in flux. Then yeah, I lost my train of thought here about that. But like, there should be a way to get there here. Like, you can pop an entire system out of this reality and then look for a place in this reality where it's valid for that spacecraft to pop in again, meaning causality allows it because the conditions are right, because that particular model that those nodes can express that validly. I think it's something like that, right?
Right. Or the idea that that our existence is governed by our position in the universe and everything, inertia and all that's governed by these information loops and this communication. And what we feel as inertia is actually the information loops kicking back at us as you try to move through the grid. So
that's like, it sort of ties in with this concept of torsion fields that some people say has been disproven and others haven't, and I think has something to it, right? The concept that physical structures essentially apply a force to space itself, and that fundamental force is actually the force from which all others kind of spring from. And I think conceptually that makes sense to me, right? The forces are emanations of something more fundamental, and you could call it a structure. It has a shape, if you will.
There's a long British tradition of being interested in this sort of thing, and so you're not the only one. There's quite a few people. Lathwaite was one of the first, one of the more famous people to really talk about this and be obsessed with this idea. So, yeah, I definitely think that there's more that needs to be studied from these sort of models. Back to what I was saying about this periodic table in terms of geometry and stuff. There's been some interesting theories put forward about that, and I'd like to see more about how those work. I have one guy coming on my show. I have a couple scientists lined up to come on here and talk to me about a lot of this stuff. One of them is actually in the chat saying that this stuff makes our warp drive makes no sense. How does what is on the skin of the craft that affects what is inside? Yeah, exactly. What kind of material would allow for this? I think we might learn that from exploring the Phoenix theory. The Phoenix theory had a theory on that was that antimatter is sort of this reverse of the time loops. That when you get the time loops going the other direction, certain weird things happen, and that there's this back and forthness of the time loops.
I would
So
think that perspective of the universe, it doesn't look like an aircraft skin. It would look like a proton or electron or one thing, right? That's what it means to bring
Right.
these systems into coherence.
Another guy I want to get on is Mike McCullough, and his inertia, quantized inertia theory. So if you go to quantized inertia, he's been writing a lot of papers, and DARPA's funding some of his research, and but this quantizinertia.com is probably the best one to look at, and that's just his yeah, so his papers. You can get this, and I'll post that. I wanted to get him on, but I also got this guy in the chat, and we've been talking. I met him through just researching. I found his name through a couple papers I was researching into some of this this new ideas of inertia, and his name's Todd Desiato, and I might be getting him on to come on as a guest too, coming up here soon to kind of share some of his theories and knowledge about this kind of stuff with us, and how it might relate to this whole puzzle, because we have to be looking at all of this. Is a real difficult puzzle because you have to know a lot about all of physics, but then you have to know all of this fringe physics, this sort of the realm of like maybe that there's stuff that physics has dismissed because it's experimental. The experimentalists have found evidence for these things, but it doesn't fit the standard model. So it's been sort of rejected and thrown out, but it might work into a different model, a newer model. So there's a lot of this going on right now, and I think this will be a time looked back on in science as a veritable dark ages, so to speak.
Absolutely. This is, I think that we're right on the cusp of a real revolution here. We're gonna, I wouldn't be surprised if within a year we see some real fundamental theory start to really revolutionize things here.
I feel like when he released this project and said we want to get people doing this, I'm like, why isn't more people excited about this? And holy shit, that's why I'm stepping up to try to do this and get people excited about this. Because the more people we get on here playing with this and sharing ideas about this, it could even be the stupid idea. That's the thing. That's the crazy thing about it is you might just program the right two functions into this, right? Like he just programmed that one thing that looked like Ken's electron in there, and it crashed the fucking program. Who knows? Maybe this is what happens. Like when you try to run this program, and it just it crashes everything, and we can't run the right program. So you can never check.
It's like I come from different I come from multiple disciplines. One is I'm extremely scientific, and the other I come from a more spiritual background. And to me, both of them are really the same. Like I'm seeing similarities between both, and I'm convinced that like you can get to this just the same using your intuition and your sense of beauty than you can like with mathematics, because at the end of the day they're kind of both the same. Like in a way, like philosophy, mathematics are at their root. You can find such strong similarities, and like intuition is a core part of us, and like our sense of beauty and order and perfection is a fundamental kind of sense that we can use to explore the universe and find this stuff. Like This stuff is not the domain of stuffy physicists who run formulas and are disconnected from the real world and like what is happening here and now. That's where things are, not in an abstract model that has worked its way into a corner. Even though it's beautiful at predicting everything, nobody has any freaking clue how it works. That's not acceptable.
So, a quick thing for some of the people in here. I was just pointing this out to I was going through some of the simpler ways to understand this stuff. Let me. I wish I could redo.
Yeah, somebody can create AI system to help connect the dots. Absolutely.
Let me.
AI system built for pattern recognition. This is what they do. So could we use automated systems to start exploring the total space of possibilities? That's exactly what Wolfram is doing. That's what makes his work so exciting. And I don't understand why people aren't like over head over heels. This is a new field of study. This is physics redone.
I see a lot of physicists scared for their careers. Honestly,
yeah, has low-hanging fruit, for God's sake. You could still come in here and be Joe Blow and find something fundamental about the universe and have your name be remembered. That's like worth it. Like that's worth it. Like as an exploration to me. Like that's something that I can definitely get behind here during the quarantine. And you guys remember that some of the most fundamental discoveries have been made during periods where people had to be shut in. Who was it? Galileo, I think it was.
it's Newton. Newton, he invented calculus, the universal law of gravitation, and optics. Well, Cambridge was on lockdown because of the plague.
There you go. Like periods of adversity breed opportunity and creativity.
And while he was creating that and doing one of the most wonderful things that humans have ever done, simultaneously on the other side of the world, on an island off the coast of Madagascar called Mauritius, humans killed the last dodo bird in existence that same year. So it's kind of crazy. There's a mix. We're terrible and a great and a terrible species.
And that's our potential, right? We have the potential to make the most amazing things and to express the highest, and also to kill ourselves with extreme, precision and efficiency, right? So
absolutely.
Probably better the former than the latter because it's so much more fun at the end of the day for everybody involved. So. Yeah,
so a couple interesting things about graphs. I want to show people just some how to do basic math with graphs. So multiplication, you could take 3 times 5. Let me get a pen that works. So did none of mine? My kids use up all my markers. Let's see. No, none of them work. Great. Oh, I could be able to do this. There we go. My orange one works. Can you see that?
Awesome.
3 times 5. All right.
There's usually one the kids don't get.
One of the ways we could do this is we could start with 3 branches off of our node, right, and create 3 nodes, and then 5 branches off of each one of those nodes, right? And then you count all the nodes in this third iteration of space right here, and you have 15, okay? You should anyway. Now, multiplication is commutative, so 3 times 5 should also equal 5 times 3. And the way we do that in our graph network is we draw 5 branches, and then we draw 3 branches off each one of those 5. That was 4. Yeah. So, and then we count up all of the vertices in this third generation of branchial space, and we get 15. So this is kind of a good way to visualize just a simple math function, multiplication, which is going to appear a lot, but also to understand branchial space, that we don't count these other iterations and these former generations of where these things came from. So we're just concerned with each moment in branchial space. That's kind of the physical reality, and that each change in our reality is one iteration in this branchial space of how the universe is doing whatever it's doing. Whether the universe is multiplying the function by itself, I don't think it's doing that.
I don't know, but I have a suspicion that there's probably a set of rules that get applied to what's happening here. Like think about the case, for example, think about the case of gravity in a black hole. Like I could model something like gravity by essentially having a function that, or a rule that, if there are more than X number of points in that look like this, I'm going to reduce that number of points by 2 or 3 points. I'm going to remove points from the graph, right?
Right.
And so when you start doing that kind of when you start applying those kinds of rules, you end up with an extremely dynamic system that could very well be able to model gravity. And I suspect that it's going to be something like that. I haven't seen that in Wolfram's models yet, but I want to.
Where there's something like, where if there's mass here, then we take out one chunk in the grid pattern every iteration. So it's kind of like that. That creates the acceleration or the falling. Why things, the distance appears to get shorter.
Exactly. So like currently Wolfram's function, that the Wolfram model, it takes 2 parameters essentially, what you want to find and what you want to replace it with. And what I want to see it do is I want to see it take an array of all of that, which is multiple finds and multiple replaces. So that I can just pass all that and like give it a set of rules. Some of the rules are going to create more nodes. Others are going to make them go away. Others will connect nodes that aren't disconnected, right? With this principle of like the graph is always evolving. It's always vibrating. It's always dynamic, because that's how it's transmitting information to different places in the graph, or to represent reality in different ways.
All right. So another thing about graphs to matrices, for the people who don't really know how to do that, let's start with a simple graph, like the one Ken said was the proton. That's a nice, easy one to do. So there's 3 vertices connected like this, right? And these loops are connected to itself. This one's connected to itself twice, connected once to this, connected once to itself, and then connected to this one. So the way we do this is we label these vertices 1, 2, and 3, and we create a 1, 2, 3 by 1, 2, 3 matrix. So it's kind of like the dimensionality of your space could also be kind of seen as how many vertices are on your thing, because that's the dimensionality of your matrix anyway. So 1's connected to itself twice, right? And it's connected to 2 once, and 2's connected to 1 once. 2's connected to itself once. 3 is not connected to 1 at all, so there's a 0 here on that side. 2 is connected to 3 once, and vice versa, and 3 is connected to itself twice. So there's how to basically turn that into a matrix, and that's the matrix for this graph. And that's a whole nother field of study with linear algebra and coming up with that kind of stuff. But this is, of course, different than the types of the branchial network graphs, which is the way to create space-time. So there's got to be some difference between this sort of function and how these fit together as particles, if these are indeed the way that we create particles. And as I pointed out, Ken showed me that how this works for neutron decay, and a couple other particle interactions that you can try if you know that this is a proton, this is a neutron, this is an electron, this is a positron, and these are the graphs for these sorts of things. This is a photon. So a photon comes and hits the neutron at the nucleus of an atom, and it creates a positron-electron pair. It splits the photon energy into this brief particle pair, or polariton, essentially inside of the neutron. That creates this W, what's that, W minus or W plus particle? that's W minus. A W minus particle and a proton, and that's sort of what we see in neutron decay. At the end of it, you get, these are the options that we come up with. This is an antineutrino and an electron. So, and the vertices you see in this interaction, the vertices are conserved always in these interactions, which kind of look a lot like particle physics and particle interactions. And they were kind of derived from looking at Feynman diagrams, and how Feynman diagrams are all branches of threes, and how you can basically create all the particle physics and all the particle interactions using Feynman diagrams.
And also, like if you're looking at, and you can kind of infer a geometry pretty quickly by looking at like threes, for example, too, because they're going to denote angles off of off of a central point. So like check out what I built real quick here with Mathematica. I put together while you were describing those networks. I kind of did a quick plot in Mathematica to see what it looks like. So I think I got it right, but you tell me if this was it. It looks like this. I think this was it. Doubly connected A and C, and C, with B having a single extra connection. So that's it, right? So that's kind of the basic structure you were describing. And then from here, this is an interesting kind of start to then trying to do like a Wolfram model, right? So like, and this cool thing about this is it's like it's really fast. So let me just grab, for example, I'm gonna just grab the main thing to do a couple of iterations of just a test that we want to.
Yep. So you're copying that code over and then plugging it in for that, so we can plot that out. Nice.
Right. So here I'm going to take this. I have this matrix here, so we're going to use that as this is our starting condition essentially, right? Yep. So we're going to our starting condition here, and then we can let's come up with a rule that is going to replace some part of this. So I'm just going to take this, make a copy of it, and I'm going to put it over here. I'll call this one find, and I'm going to make one called the replace and use that. So stuff I like to play around with is like matching a part of the structure and then replacing it with the whole of itself. Right. So that's kind of
again, these iterations, according to Ken's model, which we're going to try this and beat this thing to death if anything comes out of it. According to Ken's model, the iteration, or basically the thing that's performed is just the I think it's did I say it's the inverse or the determinant of the matrix? Basically, there's a matrix function. It's basically you take the whole matrix of this and you create this and you do this matrix function to it. It's either inverse or determinant.
It looks to me like a state machine where you just like plug in the multiple input states and this will give you one output state or something like that. I can't. My small video.
And I'm wondering how this is related to branchial space, and if
Right. And for that, like, especially if we're dealing with like, it looked like the colors were different, or did those describe polarities or something like that? With that, we can come up with rules that, like, what we have drawn right now is just describes nodes and their connections, but there's absolutely no reason that we can't add a third point or a third descriptor to this, to each of these elements that's like essentially another point, right? And that point is either kind of the positive or the negative pole. So
I want more of, I'm thinking more of like the grid network where you have like this honeycomb grid, and that you're doing stuff to it that produces these kinds of things inside of it as world pieces of the world. You know what I mean? That's kind of how I'm thinking.
I can come up with something here. Mathematica, I'm sure, has 1,000,001 different ways to do the flower of life. And look at that. Here we go. That's it. I'll open that in our online Mathematica.
Oh, this is cool.
What's that?
This is neat. I don't care if we're not getting anywhere. This is just fun for entertainment. You
Absolutely.
know what I mean?
Absolutely. Well, I mean, all of this, like this, when you look at this stuff and you visualize it in these ways, there you can very quickly see the patterns. And again, like because of the periodicity, the inherent periodicity of how all of this works, everything has a wavelength in essence. Everything has a periodicity to it that is like going to be identifiable either by its because it is like, you know, crossing a boundary condition with another kind of expression. So this stuff like is visualized very easily in this way. So let me see how I can open this up here. Ideally, I can just copy.
Another thing I was thinking, right, is what if the iterations, because you think about the starting conditions, right? Initial conditions of the universe was nothing, right? First there was nothing, right? And then, so if you have the initial conditions being there is nothing, and then out of nothing you turn nothing into +1 and -1. That's kind of like the idea, I think. And so nothing's still conserved somehow, but it's just turned into a +, -1, this sort of oscillation over
Right.
time. And that oscillation could correspond to the unitary group 1 or the circle group in the piece of the standard model that we're trying to like piece together. So
Absolutely. Like I think of it kind of like as entangled self-reference, right? So like you're saying, like there's a positive and a negative emanation. It's almost like it's like the Ouroboros, a thing looping into itself, and really it's nothing. It's a nothing. It's zero. But because there's a perturbation in that zero at that moment, it's expressing itself as a positive and negative way, right? So and it looks like there's something there, but there's nothing there, which is pretty trippy to think about philosophically. So does this mean that there is actually nothing, like from an absolute like kind of like perspective, I guess there's really nothing going on like fundamentally, which is just a really trippy to get your mind around, you know?
yeah, so this is it, the mathematical formulation of the standard model, and it's this it's basically group theory. It's all gauge quantum field theory, but it's a group theory of a product of these three groups. So this is kind of like a key or a I don't know what I call it, a guide sort of to understanding how these symmetry groups work and fit together. This is a good way of understanding how you might program this, something that can give you this, because you always have to think whatever you're putting in your program, it has to give you this somehow.
That's right.
Because that's the standard model of particle physics. That will give you all the particle physics if you have that. So that's another thing that needs to be inherent in the model. What else was I wanted to talk about? Unitary groups. There was people talking about more of. Oh, another thing I wanted to mention was Susskind's arrow fractal time, and arrows of time, and fractal flows and time's arrow. So he's got a really good paper on this right here. I'll post it in the group. People can check that out. Susskind's on all the top minds in physics are kind of converging on this in different ways. It's kind of interesting. They all have their own different approach, and I don't think any model is quite a full picture of it. We've all got little pieces of this puzzle. As Richard Feynman would say, 6 not so easy pieces. One of my favorite books.
Yeah. It's awesome. If anybody hasn't read him, which I can't like imagine based on who might be interested in this, go read him. He's freaking hilarious.
Yeah, he's great. Go read his books. Like you'll love it. You'll be like, yes, why didn't I? Give them to kids. Give them to children. And make children read them.
Like, talk about like a cool physicist. Like that guy knew how to party for sure.
Yeah, he did. With his, I wish I could play bongos with him, right? Hang out, go and smoke some cannabis and chill out in the sensory deprivation tanks.
Okay.
That's what he wrote about. It's in his book.
Awesome.
One of the world's greatest physicists. Stephen Wolfram knew him personally. Man, I think that's awesome.
That is.
Studied under him for a number of years. But
That is very small.
I always said Stephen's going to be the guy to do this and crack this. He's going to figure it out, and I'm here to learn as much as I can from people who understand this and know it, and also I gotta start playing with this program and figuring out how to build different models and see what they produce, see what we can get. So this fractal, this flower of life, yeah, I think this is a good starting point. All these things seem like good starting points for what to
Yep.
try.
Yep. There's it takes a little bit. It takes a little bit of kind of learning curve to get there, but not really a lot. I'll do my best to kind of create a bunch of different templates that we can just have online for you guys to come and peruse and take a look at. So it'll give you a starting point for your own explorations here. I think it'd be nice to have a bunch of people playing around with different stuff and kind of showing everyone else some interesting structures that they find, some like to me, like anything where I start to see kind of like out of some like chaotic looking system, some kind of I don't know, interesting order or behavior that is unexpected. I don't know what that exactly might be in this particular case. I have a suspicion when I do my grid experiment, the hexagonal grid experiments, what that will look like, because I like you're saying, all the concepts you just mentioned with having kind of an oscillation of zero, be it 1 and a -1, I feel like that is kind of one of those fundamental characteristics here, where essentially the connections between each point in this grid are their bias or their value might be is going to be changing like from moment to moment. Like, and again, I'm going to take, because since we're talking about such weird concepts with physics already and science, I'm going to go right straight to the I Ching, the Book of Changes. It's it's an ancient book, Chinese book, that essentially describes a 64 the 64 hexagram progression, where essentially what it is you come up with you have a starting value that's biased in a particular way, and if it's biased in a particular way, the polarity changes, and if it's not, it remains. And that change from one hexagonal structure to another is it essentially describes kind of the natural progression of things. So I have a suspicion that like creating a hexagonal grid and then taking the rules from the I Ching and running them in a cellular automaton might actually be kind of fun. Like that alone might be interesting, because like you never know where you're gonna find this stuff. Like honestly, like the inspiration is everywhere, and like we're saying, this field is kind of wide open in terms of what you can discover in this kind of realm of computational space.
Right. I thought it was interesting that this kind of reminded me, seeing these branchial networks and sort of this quantum space kind of reminds me of this video I saw where they captured lightning in really fast. Here it is.
Yeah.
So they capture lightning, and you can literally see it's kind of like these branchial networks where the lightning goes out and takes these it takes all these little paths, right? And then once it finds one that works, it just chooses that one.
Right. So what's going on in that can be modeled like very much. I think that can definitely be modeled in terms of like, again, a cellular automaton that has a set of rules for like, and so an advancing wavefront is going to do something right to the air right in front of it, and you can kind of advance a model of that.
The first one to hit the ground and make the full connection, all the energy travels through that ionized gas conduit. At that moment,
the general dielectric breakdown, and there's multiple attempts to try and relieve that pressure. And once it finds one pathway, right, the others just kind of give up, and then there's a full discharge in that one stream.
Yeah, but all that happens. This is like 100,000 frames a second. So that happens so fast.
Right. Yeah. Totally. But I think in the time that we'll be looking at here too, like I think an interesting challenge in this and for us is going to start to is going to be at what scale do we need to be looking at, and how much computation do we need to do to start to see something interesting emerge, right? Like if this graph or this grid represents essentially units of Planck length, then we're talking about like we need fairly large grids just to represent a single atom, right? So it becomes challenging. So we may have to like look at multiples of Planck lengths that will
Right,
work.
but another thing that Ken always talked about that I thought was interesting, and it might apply, is this whole notion of the universe being created through entanglement and quantum entanglement. That these are spatial entanglements, sort of what we were shown with these pieces of the three-dimensional puzzle, because they're entanglements that happen in three-dimensional space, and that's why they correspond to physical objects within our 3D universe. But there's also there's another graph for temporal entanglements, sort of these time entanglements, and that's sort of that branchial space. Where I see the analog in Wolfram's model to this notion of branchial space being the connection back in time to where these so these things generated from if this was the generating initial condition that brought us to this, then they're all these points in future space are time entangled back to this moment, kind of sort of through that.
Right, and I mean, if everything is like initially like infinitely like co-entangled, right? So maybe like the starting state is kind of a state of like infinite self-entanglement, and from there that state kind of starts to break down into like multiple systems that are coherent unto themselves, that then start to break down. You have like entangled particles that are still like hold an entanglement in kind of in outside of time, because like they may be separated by large distances, but still like
but also the fact that they can be like, you take these two photons, that are entangled, and you separate them these vast distances, and yet they somehow maintain this, But there's also measuring that speed of entanglement, also might give us some kind of understanding of the speed of the network, of how the network's connected.
Maybe that's like the heartbeat of like how this particular system evolves, right? Maybe there's like something even more fundamental that's like a quantized unit of time, right? A quantized element of time, and that
or
is
maybe
like
it's a dual ambiguity, or one of these this sort of fuzz function, where it could be it's both either one or the other and the same at the same time, this sort of wave function.
right. Yeah,
But
there's multiple different ways, I think, to apply different possibilities here and see what happens. So this is going to be so much fun. Like Var just in one night was able to do so much with Mathematica and all of this, and we can get really like advanced and sophisticated with this. I'm going to try to actually model out a cellular automata in Mathematica. I'm sure it's possible.
yeah, let's build a worksheet for the game of life, so we can people can review that and play with it or something too. There's probably a thing on it where people can download it. I got to do some. I haven't actually done that yet. I've just been watching the videos about it and learning about it from that. I read a couple articles on John Conway, and related to his death. He died of coronavirus on April 11th. But he left behind a great body of work, which it's unfortunate that I never even discovered him until after he died. So
It's wild, man.
I'm hoping that I introduce many more people that have never heard of him too. So
to me, he's been an inspiration for like 20 years, and I've been watching you now on YouTube for I don't know how many years you've been on here, like 10 years. And like to see your physics come together with kind of this whole new computational model, and see you recognize that it's kind of the way forward is just like it's really awesome. I think there's a tremendous amount of potential here. Like it's always how it is, guys. Like at moments when everything falls apart and everything goes to shit, guess what? There's like something amazing that happens when you least expect it. And I believe that. I believe anyone can do it. I believe we can do it. I believe one of you guys can do it if you tried. It's like
right. I believe that even if the world goes to absolute hell right now with this virus, and if it mutates and kills off 90% of the population, at least we'll we'll have this body of work that that people put together in quarantine, so that the people who survive, the elites that survive after they kill us all with this engineered bioweapon, that they'll have spaceships to go to space with, and leave us all here to. Never
Like the
mind.
men just fucking sitting around like watching porn all long, wasting our time. It's like we did something. Like we figured out the nature of reality during
Yes.
our quarantine. What did you do?
Yeah, right.
So, yeah.
Jeez. I love it. Anyways, the insanity of it all. But
We live in a
this is quite fun, man. I can see we already made $2.70, man. If we keep this up, the next
yeah.
hour we could,
We'll break $3.50 anytime. Like
a dollar an hour, man. That's
This is a work. This to me is a passion project, man. This is like this is the kind of stuff that's worth and worth investing in, because at the end of the day, what are you going to do with your time, and what are you going to what gets you excited during in life, spending money on this kind of stuff is worth every penny. So to me, this is like, what the heck else am I gonna do
I
right
don't care if I didn't get paid for it. This is more fun to me than anything that
Totally.
anything else I could be doing. Pretty much, I enjoy this stuff more. So
Sure, for sure. Right on, man. Well, this is so much fun. There's lots more opportunities, everybody, for that this kind of exploration. So, and thanks, Jeremy, for kind of taking us through all this stuff. This is pretty wild stuff.
Oh, thank you for showing us some of this, and I want to be doing one of these once a week, where we kind of have you back on. We'll work on it for the next week. I'm gonna have some other guests on. I want to try to get more scientists coming on the channel for interviews, just so I can kind of get a diversity of opinions going on this, and ask them what they think about this model, and and get them to share their ideas on other models, and educate us about some of these other things. So that's what I'm hoping to do. I got a couple guys from our experimental group, where we're still working on putting experiments together to try to test some of these fringe areas of physics, for new experimental evidence of things that might work for on all different levels if we discover something.
Yeah, man. Let's show the scientific clergy that amateur scientists still really have it going on. I mean, we kicked ass with Darwin, and Stamets is still doing good with mushrooms. So I think there's room in physics, especially in computational physics here. This is wide open.
Yeah, this is a new field, and it needs it needs.
That is awesome.
Yeah, I got a $20 live stream. $20, dude. Ask any question, and we'll here you go, man. This is super exciting. Yes, I'm glad someone agrees, man. We only got 56 people watching. I wonder if it's gone over everyone's head, but I'm super friggin' excited about this. And
this is how you do this, man. It's the theory is it. I don't want some I could spend some time experimenting and finding some cool anomalous effect and spending a lifetime tweaking that effect. Great, but I still don't know how it works, and I don't have a model to be able to do other cool stuff with. This solves the problem. This allows us to know how things work and know how to achieve effects that nothing else can do. If it can completely describe the fundamental forces in space and time as we think we can, maybe it's not a single model, but multiple describing this. If that's possible, if we can get there, I mean, the implications are amazing. We can know how to do this, not just stumble upon it, but we can know how to do it. And that to me that's what I've always wanted personally. I don't
I want to see the beautiful geometry of the proton and a black hole and all the I want to see all this all these things emerge. I want to know where 137 comes from. I want to know where this fine structure constant comes from and how we get it. And yeah, this is it. This is it. These are all those deeper questions. When I had trouble with quantum physics because it was I turned every class into a philosophical discussion, and there's deeper implications of, like, well, why does it work this way, and how does it work this way, you know
Well,
and
there's a
and it's just
reason for
shut up and
that.
calculate. No, here, just learn how to do write Schrodinger's equation, or learn how to, do.
See, you were writing the equations. That's the thing. That's
uh,
what I'm convinced about. Is these deeper philosophical questions that you're asking are the equation. They are the fundamental equation, because these questions have a questioner and a question. Right there, you have a network you've created. You've created a self-referential network. That's fundamentally important to this whole discussion. Like, because it is the fundamental movement that actually creates all things. And you have to start from there. You have to start from the fundamental philosophical basis. I'm convinced of this, because that is where you start as one, as a perceiver, as a perspective and point of view. I mean, all of that describes a vast geometry that hasn't been explored. Like, these simple fundamental philosophical questions, just those create a graph. And that is like, nobody's done that. Nobody's played around with that. Like, nobody has played around with that. And that is interesting to me too. And this can be done in this computational space very easily, because it lends itself to that, because everything, right? Every reality is occurring at all points in space. So in infinite points of view, this is happening, and it's the same activity, it's the same rules. So that's going to be exciting for us to mine. I think we're going to, it can't be boring in any case. It certainly makes nice pictures, that's for sure.
It's super interesting, because how does the universe, like, if it does work like this with all these, 10-step causal graphs where all these events are intertwined, and then, but there's this, yet it coalesces, and it drops down, like, it goes back and forward all these times in time, and takes all these paths, but then it eventually settles on this one universe that we all agree on, or at least somewhat agree on, to some
Right.
extent. Like, there's some.
And are we only in this universe because this universe is the only one that has the correct set of causal preconditions for this to emerge right now, right? Like, could we pop into another universe if we changed those conditions for ourselves somehow? Like, those are the kinds of questions I ask myself in this, because they're valid questions from the perspective of quantum physics. They're actually questions I can model mathematically, and that's exciting, because, like, if you can do it in a way that reveals what the math is all about, and, like, makes some clarity about this blasted frickin' wave function, that it drives everyone absolutely insane, and rightly so, because what it is it's just an expression of a deeper mathematics that's going on, that's happening. We just don't see the math going on. I mean, again, I'm probably touching nerves here with a lot of quantum physicists, as they might be listening to this, because it brings up all kinds of stuff that's supposedly been gone through and either discarded or solved, but I'm not so sure anymore. Like, I'm not sure.
Right, and there's part of me that, like, I like this Phoenix theory, and how like some of these particle interactions come out of it and look beautiful, but I also like E8, and how it's a little bit more complex, and that maybe it's not quite that simple. Maybe it is that simple, but yeah, figuring out these rules and relationships and how these pieces all fit together is going to be quite an interesting
Yeah, like,
endeavor.
maybe we're all moving in the same, like, reflected, like, cell or unit of space, like you're saying, the self-reflected circle. Maybe that's like the kind of the fundamental unit of space here, and there's only one of them, but it's reflected in infinity, so it seems like, it acts like there's space everywhere, but there really isn't, because it's all a hyper dimensional reflection back onto itself. It's three-dimensional, but I don't know, it's trippy, but it makes sense. Like, it makes, because you can think through that in a way. I don't know. Anyway.
I want to go back to talking about some of these other things, because there's sphere packing, and it's kind of, I noticed that this is kind of interesting, because it could be like the game of life, where the black and white spheres, but it also might be different like this. It could be three color spheres, where we have red and blue, or purple and blue, and then green spheres, or whatever, three different color spheres.
Right.
So that might be, because that would tend to make more sense because the three colors would kind of be like the third, how we have third charge and third rules with quarks and that kind of thing. That's why I like
Right.
the whole Phoenix theory, with the triangles and that it's these triangle pieces that sort of fit together.
Well, even the graph that you had me draw here earlier, or that I drew earlier with these connections where I think we're representing a fundamental particle. These have all three connections. Again, the three, it seems to be kind of like springing forth here everywhere. So I think that's a pretty strong clue as to kind of how where to find these.
So another thing I pointed out to you as I was talking about some of the interesting things I was learning from reading going over all the Buckminster Fuller stuff and all the old school watching all those old school videos and stuff. Tiling the plane. There's basically two basic tilings that will tile the plane. With a single unit that's repeated, and it's the square and the triangle. And if you take 6 triangles, of course, we know through tessellations. I had these those blocks that I played with as a kid. These ones are, I don't know if it's those are tanagrams, a little different. But these I had these blocks were 6. You know that 6 triangles make a hexagon, so that the other grid is the hexagon grid that tiles the plane, because hexagons will tile the plane. But that's of course comes naturally, because if triangles regular triangle equilateral triangles tile the plane, and this isn't showing it quite well, but if regular triangles tile the plane, then of course hexagons will tile the plane, because 6 of them
Right.
make a hexagon. But really, the only 2 that tile the plane are the square and the triangle.
Triangle.
That tile the plane with just one shape with no gaps and then no turns. You don't have to turn the piece. There's different ones that it's like this is the shape, but you got to turn it in order to get it all to fit together, or
Right.
flip it or reverse it. But this is one uniform shape that tiles the whole plane, and there's only 2 of them. That's quite interesting. And Buckminster Fuller showed that how squaring works. Like if we take 3 times 3 and you count up all the squares, there's 9 squares. 3 times 3 is 9. But if you also take 3 times 3 on the triangle, 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 times 3, if you divide up the side of the triangle and draw the lines and then connect everything, it also creates it also has that square relationship, which again relates to that Fermat's last theorem if we were to extend that to other dimensions. But
Right.
but when we extend these 2 models to the 3rd dimension, right, we find that the only Platonic solid, the only solid the only polyhedra that
Right.
successfully tiles the 3D plane is the cube.
Right.
So so I don't know if we can do this, but Aristotle actually he's falsely said that you could tile the plane with the tetrahedron, but it's actually not true. You can't. No matter what, there's going to be gaps with the tetrahedron, even if you stretch it out. If you try to tile the plane with the tetrahedron, there's gaps. And if you take the 2 tetrahedrons, of course, and you put them both together, you make that the dual invert, because the tetrahedron's its own dual. There's something called duality in polyhedra, and it's basically if you take if you truncate it or cut off the edges and fully truncate the whole shape all the way, you'll eventually get another shape, and that's the dual of that shape. But the octahedra, of course, you truncate it all the way, you get another the tetrahedra, you get another tetrahedra if you truncate it all the way. So it's its own self-dual. So I'm learning a lot about just shapes and general geometry and how to tile the 3D plane and different ways to tile the 3D plane for different possibilities for our model, because we also obviously have to tile the 3D plane with whatever kind of grid or structure that we're going to be building on and working on. And right before John Conway died, he released a paper. I think it's you can get to it off the Wikipedia page. It was in 2011. Let me see. It was 2011. So I don't know if if I gotta find it. I closed this a while ago. Let me just find that. No, I don't see it here. Let me just search for it and see if I can't find this paper that he published. Actually, I posted it on Twitter. I'll go find it on Twitter.
I'm trying to remember where I saw the video, but I remember seeing a video that discussed the flower of life grid pattern in 3 dimensions. Is essentially kind of being able to fit every platonic solid in kind of the most efficient way in terms of being able to pack the 3-dimensional plane. So I'm going to look that up and see if I can find it again, because I think it's relevant to this discussion.
Okay, there's another thing I wanted to point out. Yeah, I'll bring that up in a little bit later. Where's the freaking thing? Okay, so he had this, I'm trying to find that paper from, John Conway, because John Conway talks about basically he tiles the plane with octahedrons,
Mm-hmm.
and then finds these different tetrahedrons that fit in the gaps, but he comes up with this scheme where all these different ones can be different sizes. You just rotate them or shift them a little bit, and it changes all the size of these
That does sound interesting.
polyhedra, and that basically it creates a scheme where there's some like ridiculous number. It's like it was I forget what the number was, but it was it might have been 137. Now that would be crazy. But
That would be interesting.
but the number of polyhedra that I gotta find this because I was just reading this paper and I wanted to read it more. Tiling 3D space by tetrahedra and octahedra. This might be it. July, is this by Salvatore Turcato? Maybe this might be it. I just had it. I gotta go find this paper and I'll post it in the chat. I might even have had it in the live chat. But
Yeah, once you find it, let me know.
yeah, this was a cool one because it was talking about basically this whole way that he did this. It was a whole new playing field for a different type of game of life type thing, but it was on the 3D plane, and it was using these different combinations of tetrahedrons and octahedrons.
Right.
Which I thought was fascinating, and possibly, hold up, let me find it. I posted it on. Let me find it. Okay, I'm gonna find it in 1 second. So I know right where to look. On her page, and I posted it there. Oh man, I was talking about the game of life.
Oh.
Anyways, I don't want to take up too much time on it, and I can't seem to find it now. Maybe I posted it on my main page. Okay, so this was all right. I got a couple things that I found that I wanted to mention that we definitely need to be mentioned and talked about. So let's go and talk about them. One is Petri polygon, and the other one was this. Not the Petri polygons, but the pseudo vector, the Pauli-Lubansky pseudo vector, All right, so this has got to be another part of it. So in physics, specifically in relativistic quantum mechanics and quantum field theory, the Pauli-Lubansky pseudovector is an operator defined from the momentum and angular momentum. So this is an operator about the momentum and angular momentum, and this will it's a four momentum vector. So it's P m, which is m times v in four dimensions. One being the, angular momentum vector. So this is a key part, and how to basically create this and come up with that. And Wolfram was kind of showing this in the he was starting to talk about this in that last technical Q&A that he did with Jonathan, and where they were they went into some of these things, and he made some plots and was talking about how to get these arrows of the time to
Right.
start spinning around, and then you get a cumulative sort of effect to introduce the notion of spin. And I think that's an interesting idea. Although maybe it might be helpful to make spin a more central piece of this model, because everything seems to be spinning around something else in this universe. It's all that seems to
Right.
be a fundamental key piece of this puzzle. Everything's something spinning around something else, and it's just basically what's the biggest thing out there, and that's what we're all locked to, and we're all spinning around that.
Right.
You know what I
Right.
mean?
Some of these models kind of tend to, if depending on how you evolve, some of these models have everything kind of emanating from a central point, essentially, where you have these substructures that start to kind of emerge, in scale. But they're all it's all one giant structure that with a central node, and then that central node kind of bifurcates or splits down into multiple groups of grouped and associated nodes, and that very much kind of points to what you're talking about, where if it's doing that in branchial space, then that very much kind of points to kind of a physical space equivalent there, in some way. So again, that it's reflected in these systems that we've been looking at very clearly.
Yeah. And I like almost that some of those ideas of this, this idea of the surface of each atom or each particle being its own event horizon, or sort of mirror to the rest of the universe. That maybe what's trapped inside is like a lens through how it reflects, and because there's this information exchange across this network, which kind of is the iteration of time. And but also we have to keep in mind that there's black body radiation. I think this came to my mind immediately when we were talking about this information exchange in this network, is that even black bodies, even unless you cool something to absolute zero, it's radiating some form of energy. Everything is radiating very small amounts of energy at small and indetectable wavelengths, so to the human eye. And
Right.
if you heat it up hot enough, like iron, if you heat it up hot enough in a fire, it starts to actually glow in the visible spectrum, because of this black body radiation,
Right.
because of the temperature, and there's enough energy in it that it's actually it's radiating at those higher frequency spectrums that you can actually see. But
Yeah.
everything, once it cools back down to this. It's still giving off a little bit of even radiating thermal radiation until you freeze it. Then it stops radiating infrared. In infrared, because
Right.
it's no longer warm. But even unless it's absolute zero, everything's radiating a small amount of radiation. It's sort of this property of matter. Everything in the universe is doing this, and I thought that was super. This is got to be a key piece of the puzzle, because it's sort of this information exchange that keeps everything relevant and keeps everything talking and knowing where it all is, and that I'm still here, I'm still moving, I'm still and this
Right.
is kind of evidence that we see in the physical model of this communication of the information exchange constantly across the network.
Right. And if the state of each of these kind of nodes or each of these points in spaces is is essentially vibrating or like kind of changing from one to the opposite in a way, where like each point has a kind of is an oscillation, then it makes sense that it kind of at rest you're still going to see you're going to see effects from that. You're going to see this kind of the vibration of this kind of this matrix play out in essentially, like black body radiation, like you're talking about. So it definitely fits there, and that's kind of what I'm going to try and model, is essentially kind of like what's this grid look like? Can I achieve some kind of dynamic equilibrium where like unperturbed the whole thing is essentially each point is vibrating, but it's all kind of in a grand coherence where it's all vibrating in coherence, right? And as you perturb a location on that grid, because the grid's vibrating inherently and the perturbation happens at some multiple of that vibration, not naturally normally, because we're dealing with these scales where kind of like it's, what's actually happening is maybe multiples of this vibration, right? So you're going to see this point in space kind of become perturbed, and those perturbations themselves are going to have an effect back on what's perturbing it. Kind of like, it's kind of like the pilot wave theory that has been supposedly thrown out completely, which to me is a beautiful it's a beautiful model, and I think worthy of like perhaps using some of the kind of the concepts there, because they make sense. Like this concept of this kind of like this infinitely refracted space that's refracting back like reflections of itself back onto kind of what's happening in local space and affecting that, and making it look like it's it's in two places at once, or making it look like we can't those are, I don't know, that's where to me it's exciting to explore that, and we can do it with Mathematica. So
and what's the other one? Bell's theorem. Yeah, Bell's theorem. They were talking about Bell's theorem too in one of the Wolfram live stream. It deals with like polarization filters and how you add the third filter and suddenly like things come through again when it makes no sense.
Yeah.
Why it should do that unless there's quantum actions going on within the system. And that's sort of explained through that linking of branchial space and causality and whatnot. It's not intuitive. It's somewhat complex, but it's again not outside.
So I think our challenges will be finding ways to visualize that branchial space. Like how do you use the concept of perspective to look at a network from a particular perspective, see what effects might be there, right? That's what I'm really interested in looking at. Is like that's where we're going to find our clues, and so we need to have ways of very quickly like putting a telescope on a particular section of a network and seeing how it looks from this angle, right?
And also these the idea of these black holes and stuff. I one of the questions I had about matter and energy is we have this equivalence factor of E equals mc squared, which tells us that matter is trapped light or trapped energy that's traveling at the speed of light. That's how we get its energy, by multiplying it by the speed of light. It's not a little bit less than the speed of light. It's actually moving at the speed of light. So is it actually moving at the speed of light? And what does that mean physically for the system? And is there, this sort of, what happens in Einstein's field equations in general relativity is this, the event horizon of a black hole is determined, the radius of that event horizon is determined by this radial relationship called the Schwarzschild radius.
Right.
And it's given by this the gravitational constant times the mass of the black hole over the square of the speed of light in the same way. And so sort of there's been some interesting models of using this Schwarzschild radius on the proton, on saying that a proton's basically like almost like a black hole, because if it's trapped light that's traveling at the speed of light, then like it's kind of like a black hole. It kind of might work similar to a black hole, but it's not quite a black hole. Obviously it's not, gravities and space-time isn't being warped completely inside of this, but maybe it is on some kind of other level where in this sort of bubbling effect, which
Well,
is
like a
kind of
causal, like a like basically there may be some type of like causal loop that or something like that. It happens at that scale where if you take the two systems that might normally like exhibit behavior in a particular like direction or polarity, and you bring them close enough, that may actually either reverse that polarity or like you may cross these phase transitions like you're talking about, where all of a sudden a photon can become trapped because it's circling on itself or something like that. It becomes
essentially what you're saying is it's losing degrees of symmetry.
Right.
It's losing its degrees of freedom, and that's kind of what we've determined, this basic structure of matter theory of how to explain gases, liquids, and solids is the phase change, the physical phase change happens because of a loss of degree of symmetry.
Right.
For example, how it works is, like a gas is a gas because it's got free symmetry. It can move translationally, it can move rotationally, and it has all the degrees of freedom. Whereas in a liquid, right? In a liquid, it's trapped inside it can't move translationally. It can't move kind of bouncing around anywhere. It's not floating. It's kind of it's heavy and sticking to one another, but it still has rotational freedom. So it can still spin. And when it loses rotational freedom, it freezes inside of a lattice structure, and then it becomes a solid because it can no longer slide and slip over each other. You get it? And that's kind of like the how to explain gases, liquids, and solids, the three phases of matter in terms of symmetry, in terms of math, pure math. So it's lovely. I love it.
Oh, it's really cool. And then like right as you add energy to the system, which is essentially like mechanical vibration, right? If you're adding heat to the system, that pushes the entire system to those phase transitions, and again, maybe that's like a model that kind of at a model at this level that we're looking at. Maybe it's these kind of, it's essentially these atoms are shaped in a particular way, and like given enough kind of vibrational energy, they can shift from one position to another freely in this kind of like geometric grid that allows them to move. That's kind of what I see, because again, like if space is quantized and time is quantized, and we're dealing with each cell has a shape, like literally, like it has to be that way. Like that's what the ramifications of a quantized space are, right? Is that each cell has boundaries and has a clear shape and definition, and the shape of that cell is fundamental to the way that things move through it. So
this is the whole idea of atomos. It's like, what's the most indivisible piece? Is it and according to this theory, it's a vertex. It's just a point.
Right. So maybe like reality is like a big giant fucking Tetris puzzle, and reality matter's moving through it like in the way that like the rules prescribe it. It looks like it's continuous motion, continuous time, continuous energy gain and continuous heat rise or whatever, but it's all actually quantized. It's all actually runs like a computer. It's trippy. Like it could all be like, talk about like, what, like these philosophical things keep coming up, like, together, like, the concept of like living in a simulation, living in a computer. We very much are, in a way. We live in a computer that's computationally irreducible. So you can't, you can only model it by doing it. So I'm not sure that you can actually take the totality of what's going on here and reduce that any further in a computer. The computer would have to be orders of magnitude larger than this universe to do it.
Right. That's the whole idea of the why he kind of pokes holes through simulation theory, and the whole idea is, are we running just in a simulation, and are we in a simulation? It's like, yeah, I mean, it's kind of egocentrical to think that we all are. Maybe if you think that you are,
Maybe you think that you're living in a universe where the Planck length is a tenth of what we think it is. Like and that's the only case in which I think might be the case is like that universe has a much smaller Planck length, and that thus has a finer resolution, and ours just looks bigger because we are living in a split. But again, those relationships between the size of the physical universe and the simulated universe, assuming computational irreducibility, means that there's a direct physical relationship between those sizes. You can model it depending, like the short size, the Planck length would have to be orders of magnitude smaller in that other theoretical universe for this one to be modeled with any kind of, for it to be done. It's not I mean, I don't know. It could be it could be turtles all the way down for all I know. But you see what you can from this perspective. So,
yeah, definitely interested in exploring this more. So glad that I that Wolfram published this and came out with it the way he did, and is doing it this way. It would never be able to come together quite as quickly, or I think as collaboratively as if he had done it, through try and approach things the traditional way. And of course, there's going to be so much resistance to new ideas and new approaches and stuff that we've already seen a lot of that.
Totally.
So,
well, the nice thing is that we don't who gives a shit about what the other people think. As long as we're having a good time and we're doing some valuable work here, and getting somewhere, then then we'll have the last laugh if we can create a model that spits out all of this stuff, as emergent here.
That would be awesome if we did it, or someone that even if someone I inspired through my video figured it out. It was like, oh look, I was watching you and listening to your ideas, and this one thing you said was it. Maybe there's something in here. There was a bunch of everything else is wrong, but this one thing that was like, oh, that kind of worked.
Stood out totally. And at the end of the day, I want to contribute, like we were talking about, contribute all this back to the main Wolfram project. This is like a collaborative, open source. This is how science needs to be done. It's got to be open source, just like our software. Our science must be open source, and all of this must be a collaborative effort with I don't, as an amateur, I don't really care about whatever the hell people in the science industry care about. So I just want to do something awesome. And there's a lot to be said for people like us who are doing that. We have interesting ideas. We come at this from different perspectives. We're a lot of us have a lot to contribute here. All of us can see something from our own unique perspective that you never know what will come out of that. So everybody here who's listening, if you're at all inspired, play with this seriously. Grab one of these things that we do and run with
this.
This
use this programming language. This is your microscope. Well, the rest of these mainstream particle physicists and everything, they've dumped all their money, billions, into the Large Hadron Collider at CERN. That's their microscope for looking at things, and they want to just build bigger and bigger particle accelerators to try and see, more and more of these things that are going on. I think we got a clear enough picture now of everything that's going on down there at this level, and this is this is the tool we need now, and I think that scares the shit out of all these people, because they're going to lose all their funding and all their grants when people realize that they can do this from simple geometric and puzzle pieces on their home computer, and
Exactly. Why do you think they're so angry? Anyone that reacts with there's no reason at all to react with anger to any of this. So anyone that does is having a paradigm challenge there, and that's why people get mad at this, because they have all this invested time in this. Throw it all away. You can always relearn all of reality and learn something fundamentally new.
There's no reason why anyone who's interested in educating people should be against this and what we're doing here, and what Wolfram did, and what's this whole physics project. And the fact that if any of them are, it should just show
You
that
just don't have any imagination. You're not looking around at the possibilities presented in these systems that are the way that reality works. Reality from each little all points of perspective, animating some grand thing that occurs. So it's going to be, from any particular perspective, the conditions of that perspective will be limited. So it will be playing out a particular set of rules that are just encoded in this, in all of this. And we just have to find those rules. We can find them, and like, there's nothing wrong with that approach. Like, and I know philosophically people get mad at this because they did all that hard work of like learning all these fucking physical laws and like all this detailed work, and like you have just created a tower in your mind and it took you 10 years. I appreciate that. That's beautiful. That's wonderful. But you know, like don't use that tower to bludgeon people that come at it from another perspective. Like, because there's multiple ways of seeing reality. Like, reality is reality. It doesn't care about like how you see it and how you come at it and how you understand it. You know, it's and so like, yeah, it's, again, like that's been my attitude with all this, and that's certainly enabled me to have a good time and learn some interesting things at the very least. So
Right. Again, I think another project needs to be from our particle physics. We need to get someone who's real good with particle physics to just basically write out all the particle interactions, you know, and the Feynman diagrams for them, and come up with like a whole library list of all that, and then I'd like to go through all the Phoenix theory and test that to make sure it all works in that matrix formalization with those, you know, graphs where you just plug them in a matrix together and plug away, and it creates all these particle
like
interactions through that. That would be cool.
Wouldn't it? Like, there's got to be somebody listening to this right now that's either like a physics student or like knows one that might be interested in this stuff. And though I think those are the people that are gonna like really make a difference. Like, you are fascinated by physics and you've already have a good solid grasp on you know, fundamental theory, but you know it's bullshit at the end of the day, and you want to find out how. Come play with this. Like, come work with us, and you know, like reach out to Jeremy, connect with us, and like help us with this stuff. Like each person has a missing piece. I know how to do the computational stuff. I can make this stuff, you know, all day long, but I'm missing certain fundamental understandings about physics that I need. You know, like, we need each other to make this work. So let's do it. Like, and if there's people out there that want to contribute, now's your opportunity. I feel like I personally have been waiting for this opportunity for 25 years. That's how long I've been studying this stuff and waiting to like jump in at the right moment in a place where I can contribute. And there's somebody out there right now who's in the same position. Like, so come
Yeah,
play with us.
that's why I invited you on. You were the dude. I mean, I know a lot of people, but you were the dude for this job, and glad to have you on board and be working with you on this. So I wanted to go again to show people these Petrie polygons. These are really, really cool, and this relates to, of course, Eric Weinstein's geometric unity theory, because he kind of wrote some of this stuff on the 10-dimensional demicubes and some of this stuff. Really interesting. Some of this stuff goes back to the 40s, with you know, Coxeter writing the original stuff on these Petrie polytopes, but it's recently kind of been expanded with Eric Weinstein. Right here, his publications in Math World, on the Gaussian graph, the 600 cell graph, the 120 cell graph, 24 cell graph, the cross polytope graphs, and the hypercube graphs. Again, the hypercube graphs are quite interesting and might provide some path insight to approach. Again, yeah, Weinstein's stuff is very interesting, coming up with this sort of geometric unity theory, and that's again related to what I said about testing for Matt's last theorem. You know, maybe this might be it, where we finally solved for Matt's last theorem with this geometric unity puzzle. I don't know if we ever can solve it really, because the amount of iterations you'd have to blow it up to make that proof. It's such a hard proof to really, you know, prove.
Right. Totally. Like, where do you run into, again, this concept of computational irreducibility? No way to actually do the proof, no way to actually prove the thing unless you actually do the work to prove it, right? You have to advance the system to that state to prove it, because it has a set of rules that can't be rewound, essentially, right? That's the premise behind kind of computational irreducibility. You can't get there unless you go through the steps. And I think a lot of these systems will probably reflect that, right? Like you're showing here. It's like you have to blow this model up to that size in order to kind of prove that it's doing that.
Sorry, this is Eric Weisstein. Sorry, I've been saying this wrong a lot. Not to be confused with Eric Weinstein. So Weinstein isn't the guy. All right, so I got these guys confused. See, I was watching on the Eric Weinstein interviews on Lex, and I was thinking that this is Eric Wolfgang Weisstein, and he's the guy who created the Math World. So good. Thanks for bringing that to my attention, because I was, these are two different guys here, and very similar names, Eric Weinstein and Eric Weisstein, and both doing a lot of stuff in geometry. So Weinstein is the guy doing the geometric unity stuff, right? I thought he was doing geometric unity theory. And that's, see, geometric unity. So in May of 2013, Weinstein gave a colloquium talk, geometric unity, on the potential of a universe theory of physics. So the 14-dimensional space. So yeah, he has this whole thing, but that's different than Weisstein, who came up with all these hypercubes and stuff. So, that's interesting. Thanks for bringing that to my attention. Someone in the chat did that, and I'm sorry to both of them for making that confusion.
Interesting.
But I'm sure they can see the mistake and the error. But yeah, that's interesting that these are two different people. So we'll have to make that clarification going forward. And
interesting.
All right, so I want to grab it's getting to be past the almost 2.5 hour mark, and we probably got a half hour left before we wind down. So I want to bring some guest callers and friends and stuff on Skype. So I'm going to be on Skype. If anyone wants to call me on Skype, they can call in and ask some questions. I might go grab I'm going to go grab a beer because it's about that time to start winding this down. So, and we'll start talking about some other stuff. So anything else you wanted to add, Sebastian? Our show is...
I think that we've covered quite a range of topics and ideas here. And I know I certainly am going to go back and actually listen to this myself, because I feel like we've gone through about a dozen different kinds of really fascinating topics. And this thing is full of, possibility. And the only thing I really have to say is I'm, totally excited to be doing this. And I encourage anyone else who is watching this to get in on this. This is your opportunity to be at the beginning of a real revolution in physics and in computation. And there's not a lot of opportunities like this. I lived through the beginning of computer science. I'm in my mid-40s. I've been around for a little while, and so I got to live the beginning of the internet. And I got to tell you, there's nothing like seeing kind of the beginning of something like that. It's exciting. You feel like you're part of it and you've contributed. I think the same thing is happening here. So get in on this. A lot of people are interested. I see a lot of you guys online talking about this. Great, you have good ideas. Now do something with it. Even if it's 2 lines of code and it makes pretty pictures and it makes you think about something in a different way. That's where you're gonna push yourself to that edge and see what kind of creativity comes out, because that's where awesomeness is made. So that's pretty much all I gotta say about that.
Nice, and it's free 14-day trial for Mathematica. So why not?
Yep, absolutely.
What do you got to lose?
Tell them that Alien Scientist sent you for sure. If you're gonna go get a license of that, I want them to know that we're driving traffic their way.
Yes, that'd be cool. Yes, beer time.
Sweet. All right. Well, thank you everybody for listening to me blab here, and thanks Jeremy for giving me that opportunity. I look forward to doing this again soon.
Yeah, this was fun. I thought it was awesome that I tuned into Wolfram's live stream earlier today, and I was dropping a bunch of comments talking about how we were going to be doing this live stream and trying to teach this and get involved with it. And they were like, "Oh, that's awesome! Send us a link," and then and posted on Twitter. And so I did post it on Twitter, and Stephen Wolfram liked it. I don't know if it's him running the page, but I just want to show that.
Okay, I feel like one of those rock and roll.
What's up, Jeremy?
We're officially rock stars, man. He liked the tweet, so.
Hey, man.
I hope he was watching, and I hope we give him the idea that helps him like figure this out and.
Multiple rules and rules that grow or fit and also stop motion. There has to be some type of dynamic equilibrium that can be achieved there, and I don't know. There's so much.
Mark, you want to mute your mic?
Oh yeah. 1 second.
So I got Mark on here, my buddy from Falcon Space, and our lab coordinator down in New Jersey.
All right, so here's what's going on. I'm actually at the lab right now. I was getting the shower fixed, so we could have a little accommodations here.
You could have me come down and tile it.
when foreign scientists come down, yeah, it badly needs some tiles. I just fixed the hot water heater had a blown element, and I put up a curtain and everything. It's a pretty easy job. You throw a couple tiles in there. Nothing too fancy. Maybe I'll make it into an Airbnb.
Right.
But what's going on with the experiment is that I couldn't verify that the signal generator is working. I tried with my oscilloscope, and I got no signal whatsoever. The output for the pulses has like a signal port to show you what's happening with the pulses. That does work when I connect it to the oscilloscope, but the signal itself, the gigahertz frequency, I don't see anything showing up on the signal generator. So I made contact with this company here in Jersey in Farmingdale called All Test, and they specialize in used high-end equipment. And they got a couple signal generators there that go up into the no, not signal generators, signal analyzers that go up into the gigahertz range. They also have a 200-watt amplifier that I was looking to borrow or rent from them, and they got pretty good prices. So that may be the place to go. I'm already in contact with one of the technicians, but because of coronavirus, they're working at like half capacity or less. So you really got to push your order through to make it happen. And that's what's left to the Alzaphan experiment. Once we get all those pieces together, we can try it out and see if it actually works, and give you some final results on that end. I heard your guy Wolfram was talking earlier about coherent matter. Is that the same concept like Alzaphan?
In what regard?
In regard to inertial mass shielding and gravity shielding.
I don't know, because I don't know the answer to that quite yet. There are elements of the Wolfram model which I said correspond to things like wormholes or warp drives and things that could be pulled out of it. Yes, they work a little bit differently, but again, we don't have the clear model because we don't know how to produce particle physics out of Wolfram's model yet, and we don't know how to produce all the things like spin and charge, and there's quite a few pieces missing. So that once we're able to sort of elucidate that from the model, we'll be able to see if there's more of these analogs to other areas. But this is certainly this is stuff in the experimental, and I'm glad that we're replicating these experiments to see if that we can get these effects to work, because then we'll help to know if these models or these ideas, sort of correspond to physical reality through experiments. So it's good that we're attacking it on both ends.
Yeah, I agree with that. I actually got a call today for Falcon Hybrid for the battery company. Somebody wanted to buy a couple dead modules, and I asked him what he was using it for. He said he wanted to make a hydrogen fuel cell. And we had a long conversation after that. It went on for more than an hour. And this guy was all in on, Area 51, anti-gravity, all that stuff. He seemed to be very much in the know. And I got him to add WhatsApp to his phone, and we added him to the Falcon Space WhatsApp group.
Oh, geez. That's weird how these people are finding you not even through those channels. But, and I'm interested in working with people that, are going to push us further along down the road. The people with the scientists and the other connections, to laboratory equipment and know-how and experience and knowledge, and even some of the people that have been in our group, we got to reach out and I'm going to be bringing them on the. I'm going to get Todd to come on the show, and I love Jeremy. Jeremy, get on the show. Yeah, every time Jeremiah gets on the show, definitely. Let's add him to the call.
You should just give Todd a call. I mean, he's stuck at home watching birds lay eggs on his porch.
I know he's got to get a little he's got to get a haircut and a couple other things. He said, because we've all been sitting on. He's like, oh my god, I gotta shave. It's like, and then I think he's got a lot of stuff going on too. So we'll figure out. We'll make a time to get Todd on, and I want to get a couple other people on too. I'm trying to get Sky on too. The guy we had on last week. I just added him to the group call too, so hopefully we'll get him.
That was an interesting conversation.
That was, and I wish we had kept it going. I wish we didn't hang up after when we did. I wish we had kept it going.
I had a couple.
That's okay.
With him since.
We've got the recordings too of some of the ones that we've had, so we could probably make that a show and just post those things. He gave permission to have them posted publicly, so we have those recordings.
Nice, yeah. All right. That's sweet. I ever kick myself in the butt when I don't do. I should screen capture, and I have like 4 gig hard drive, a 4 terabyte hard drive, and I don't have to worry about room or space ever. But I was like, why didn't I record? Why wasn't I recording that? You know what I mean? It's always the good stuff too that you're not recording.
Always. And there are so many phone calls that I've had with serious, brilliant geniuses that I was just, kicking myself because I knew the stuff that I was hearing from these guys was so far beyond where I was at the time that there was no way I was going to possibly remember it, because you can't really remember clearly things that you don't understand at the time that you're hearing them.
I know.
And I'm like, oh man, if I could have only captured those moments.
We've all had those experiences, but the thing is that those moments occur naturally, sporadically, and are genuine. And the second the recording device comes on, bam, all that goes away. And you can't predict when those sporadic, organic moments of genuine dialogue and discussion are going to come up. They just happen.
Fact.
Well, that's kind of like I've always liked the idea of just having a recording device that on my person, or just with the ability to hear whatever my ears can hear, which would of course involve some kind of microphone that was actually in my ear. So if I'm listening via headphones or something else that I'm experiencing, no matter what it is, it's recorded. If it's a conversation with somebody else or even a phone call, that would be really awesome. But just have it basically going 24 hours a day, and it can recycle its own memory. But if there was something during that day that happened that I wanted to recall, because it's always happening, you don't have to think about pressing record, and you're not really conscious or worried about having to activate this device. You can just log those conversations. It's something that I've been wanting for a long time. Cell phones should have the ability, in my opinion, to do that at this point, and it'd be super awesome if there was an app and the ability for memory compression live to do that for, say, cell phones that have 128 gigs. Because realistically, how much space do you need to just write 24 hours of MP3 data continuously compressed? But
hear me out. We make a electronic device. It's kind of like Bluetooth, right? and it hooks up to your cell phone via an application of software, and we sell it. And we basically make scouters from Dragon Ball Z because Google Glass did it wrong. The Virgin Google Glass versus the Chad Scouter.
I'll tell you what, I actually think the scouters look pretty darn cool. I
Yeah,
would not at all be embarrassed to wear something like that. It's
Yeah.
kind of future and badass looking.
yeah, exactly. Like, here's the thing. If we're going to get the Cyberpunk 2077 over-the-top anime future, we may as well embrace it.
Yeah, dude, the scouters look way cooler than Google Glass.
Yeah.
Just saying. Plus the field of view, man, you can't beat that.
Oh, yeah.
What are they called? The Scouters? Scouters?
Scouters from Dragon Ball Z.
Scouters.
It's a biofield measurement piece of electronic equipment that you wear over one eye.
Yep. Okay. Gotcha. I'm not as familiar with Dragon Ball Z, so that's cool though.
Yeah, that's basically what they look like.
Yep, and it's like Terminator overlay. It's a target acquired, height,
Exactly what it's
weight,
for. Yep.
weak points identified, and all that.
Yeah, precisely. But those things kind of look cool. Like when you're wearing one of those things, it would look pretty darn neat.
Yeah, well, that future might be coming. Who knows? That sounds much more desirable than some of the other dystopias that we've discussed as well.
Well, I mean, Google tried to do it with Google Glass, but they made it look like some hipster garbage. If they're gonna make this electronic
Dude,
wear
exactly.
stuff, I mean, embrace it. Embrace it for what it is. Stop trying to tiptoe it and make it all hipster to appeal to normies.
Dude, it literally does
Yeah,
look like
yeah,
some hipster
for
garbage.
real.
I swear to God,
It
if you're not
is.
wearing that with some kind of like crosshatch shirt, it just doesn't look natural on you.
Mm-hmm. They gotta really embrace it and make it a big, huge.
Other than a pair of glasses, what other option do you really have to reflect something into your eye? I mean, we're not at the level of cornea implants or, on that level. So it has to involve some sort of glasses.
We could have it look like Cyclops from X-Men.
Yeah.
There
Or
we
like
go.
Bort from The Day the Earth Stood Still.
Yeah. Yep. That'd be awesome.
Or the Borg from, what was it, Star Trek.
All right, so we quickly switched gears off of all the Wolfram stuff and this new math and physics combined theory of math and physics and of space and time is just space. And
The Wolfram stuff and its ability to make predictions is pretty exciting. I mean, there's still a lot yet to figure out, but it's a new way to look at things, and that's always a good thing.
There's a lot of new models. General relativity is being called into question now, as it should be, because that's how good science works. There's a lot of new, Wal Thornhill, Dr. Don Scott, Emmanuel Velikovsky. There's Wolfram, and so many people are creating new models, alternatives to the Lambda-CDM model, alternatives to the standard model. And these alternative models are in many ways just as functionable, arguably even more accurate and more functionable in many ways. And the future, as it turns out, we're not narrowing to a universal field theory. As it turns out, the opportunities are opening up and blossoming. So, academia has tried to stifle this, but honestly, I think the future of physics and science is going to be paved by engineers who just don't give a fuck.
Right. I want to talk more about your idea about us getting like our own like commune, basically our own place set up where we have a town where we'll literally go and buy out this whole town so we can own the whole county government and just like have our own commune basically set up to just do science and all the stuff that we want to do where they can't touch us.
Well, I mean, this is a plan that I've been working on for about 2 to 3 years, and we've already purchased the land and acreage. I already have a team. We already have a team of about over 20 men backing this, financially and otherwise, and they're putting in big money of their own money. So, I mean, it's not a lot of money, but it's big money to them. We're talking about between $4,000 and $20,000 each on person, per person co-signing.
Wild.
Well, the thing is that these are basically men that don't really have fiduciary responsibilities to families, and because of that, they have the luxury that basically they're able to, as Terence McKenna says, to find the others. And we've gone out of our way to find the others, and now we're basically, the time for talking is over. Now is the time for action.
Absolutely true. Absolutely true. I've made the same dedication to not have any other family that depends on me so that I can pretty much pursue these interests in this research.
Exactly.
That's where I got screwed.
Well,
Yeah, man, I don't know what you were thinking.
What I would like to emphasize is flying saucers is ultimately an electrogravitics and, infinite energy via scalar waves or whatever. That is definitely the long-term goal. I do not disagree, and I am all for all the research and all the development into that. The problem, however, is that right now we're basically a bunch of LARPers in our houses that, are kind of coping with the situation that we're handed with at life just by reading up all this stuff because it's the most that we can do. Well, no more of that.
Talk for yourself. I'm actually in the lab with all this equipment.
Well, so I know you are, Falcon, and
I'm in my own lab at the same exact point. I have all this stuff set up too. I've got an 80,000 volt power source sitting behind me, and I'm working on an ultra lightweight power supply right now. That's it may be a record breaking lightweight watts per gram.
Nice.
88,000 volt output micro.
Wow.
Nice.
So
Ooh,
I
that's
think
a
it's
lot
going to
of
weigh in at like 16 grams at 88,000 volts and produce about 25 watts.
Nice.
Which means that it's way within the classification to
right.
fly itself on its own ion craft. And that's going to be awesome, a self-powered ion craft.
Are you going to go for vertical takeoff and landing, or
Absolutely, yeah.
Yeah, VTOL's the only way to go for something like that.
No, you can go into an airplane mode. It's actually much easier in the airplane.
Oh yeah, it requires 13 times less energy. That MIT plane was a joke, man. 5 pounds. That thing weighed 5 pounds. It was ridiculous, and it only flew for 11 seconds. Meanwhile, Ethan Krause is there with his VTOL.
That wasn't.
lifter.
No, that wasn't flying at all. It was launched.
It was initially launched. It was initially launched, but that was the first video. And if you take a look and research them, and you see the series of videos that came after, you can see that it actually does start to gain altitude in the longer gym test after they got the power supply issues fixed. But the first video, no, it was just launched, and it basically just falls with style. But no, they did get it flying. They got it to fly for a total of like 15 seconds or something like that, and claimed that the limitation was the length of the gym, which is obviously BS. I mean, like I said, meanwhile, Ethan Krause is over there with Ion Air, and he's got his craft flying now for 1 minute and 20 seconds plus VTOL all the way. It's just a lifter with a extremely efficient lightweight power supply strapped right to the center, and all of the corona wires just strapped right to the top of it. And the key there is spacing. It's extremely lightweight, but yeah, Ethan KRAUS.
KRAUS.
Yeah, or SS maybe it is. Yeah,
ion propelled craft.
So this guy is pretty much, in my opinion, the premier person right now working on VTOL ion craft technology, because unlike all of the others who have patents and various other 3D models and all that, he's actually got a working model that does fly in. Now, like I said, it's self-powered for 1 minute and 20 seconds off the table. So that is huge. I mean, that makes MIT look like a joke.
Yeah. And MIT's already got more thrust than per energy level than a jet engine. And this is
and Ethan is like probably 20 times greater in his.
Wow.
If you were to strap that thing to a plane configuration, he could probably keep it in the air for, I would want to say, 10 to 12 minutes.
What's the efficiency?
The specific impulse, it's something on the order of like maybe 50 or so times better than jet propulsion.
Okay, the specific impulse, that's interesting, but what I'm asking is what's the actual conversion efficiency?
Right now we're limited sort of to 1.5%, and that gives us VTOL already at only 1.5%. The reason why the inefficiency exists is because most of the ions fly off of the corona wire in the opposite direction, and the corona wire actually repels itself against the field, so that causes it to be pushed down against the field of ions that are flying upwards. Meanwhile, the only ions that are actually useful are the ones that fly downwards and are attracted to the collection grid, which pulls itself up into the ion cloud. Now,
how energy dense in terms of megajoules per kilogram is your current energy source?
I have not calculated that out yet, but it's something that I'm going to be working on with the new power supply, and I'll be able to give you those numbers after it's built. So yeah, I don't know exactly how much the solder is going to weigh yet.
You should also consider trying my design for the ion lifter, where you have a sort of brush of high voltage wire, and the voltage comes off of the tips. This way you can direct them all downward and have less upward loss.
Well, that's one way to do it, but the other thing that I really wanted to do instead was to make an ultra-fine mesh screen out of these super fine lightweight wires so that I can form an ion trap and force all the ions the same charge as a screen to go away from the screen, so that way they can't escape outwards into the atmosphere. That would involve ducting. It would involve encasing the entire thing in some kind of framework, and that framework would have to be light if I still wanted it to be able to lift itself.
I also like what David Parez is doing with the fractal antennas for his design.
Oh man, that's something real right there.
I thought that was cool. Ever since I saw Nathan Cohen speak at MIT and talk about fractal antennas, I was really intrigued by that idea.
That's just one more theory that basically states you compress space-time with radio waves. And it goes in perfect concert with exactly the things that we've been talking about with the electric model of gravity basically being explained by motional fields instead of, say, fundamental forces.
It's just a better way of interacting with these fields if you build your antenna from these shapes, you know.
David Perez, for those who don't know, is Space Warp Dynamics out of I think it was South Dakota, right?
Yeah, I think so. South Carolina, maybe.
Oh no, South Dakota. He's in the Dakotas, like in the center of the country, toward kind of.
Okay.
And he's also a professor.
I want to get him on. We're gonna get him on at some point too. I got to reach out to him because he's a cool guy to him, and we should definitely be one of the people we get on to talk to. This will be fun.
I reached out to him like a year or two ago. I mean, he's going in a totally different direction to anything we're doing, but it's interesting to have people in all perspectives. He's talking about thrust when we're talking about inertial dampening and inertial mass cancellation and gravity shielding. He's talking about actual thrust being observed, and it moves in any direction that the thruster is facing, which makes me think it's more of an electron rocket than real anti-gravity, which is still useful, for what all these projects that we're doing. But I don't think it's actual anti-gravity.
Well, it was long disproved. That whole it says right there on the thing that the whole link between anti-gravity and this electric field forces was started by Thomas Townsend Brown, who was kind of promoted it through the UFO community for a number of years through his company Overland Associates or whatever it was. I have a bunch of stuff. The Vero Corporation and a couple of other companies that Thomas Townsend Brown started, and he piped up this idea and sold it to a lot of different aerospace companies who experimented with it and sort of rejected the idea. And that's sort of where I feel it's with until someone can prove a link between gravitation and electrostatics. High voltage electrostatics, until someone can verifiably prove a link between those. I'm pretty sure that idea has been discarded.
Well, in terms of links between gravity and electrostatics, that we can actually display with some experiments here that we actually have been doing. Nam just did one earlier today, in fact, where he's got a piece of paper shielded behind Lexan glass moving as a result of a fast discharge, which does explain electron momentum transfer through that sample, and then the compression of space-time due to the electric charge and its motion.
Well, I mean, right now, there's, like I said, there's a bunch of different cosmological models on how the universe works, and we're talking about a lot of things that are mutually exclusive depending on which model you're talking about. So, when we're talking about electrogravitics, then electrogravitics specifically can't really have anything to do with space-time and conventional relativity, because they're kind of electrogravitics is a technology that's, its principles of operation and modus operandi operate off of a more plasma-based cosmological model than a time-space-based cosmological model.
Actually, the term electrogravitics has been coined by Thomas Townsend Brown, and people connect it with the ion-wind effect. But electrogravitics fundamentally just means a connection between electricity and gravity. And anything that we're going to create will be using electricity. We're not going to be, it's not going to be horse-drawn wagons that make anti-gravity. It's not going to be springs or kinetic energy. It's going to be electricity that somehow creates this effect. So everything we're talking about is really electrogravitic.
Well, I mean, it might be electricity as a source of converting power, but we're not really sure, because we might end up just pumping electricity through something like a multi-cavity klystron or a Rodin coil to spool up a fluid or create an impactor or something to basically create a secondary field force that's not necessarily purely electrical in nature.
Well, exactly. You do have a really good point there, because when you combine the momentum or the inertia of an actual sample in motion with an electric and magnetic field, then you can convert that momentum or that inertia depending on the direction of the field that it's experiencing. So there is something to be said about the combination of forces to create a tertiary force that's significantly stronger than, say, just the electrics alone.
Correct.
But the other thing that you need to remember is electrons can take the place of that rotating mass. So in certain configurations, if you can get them moving fast enough, like accelerators and whatnot, you can use the mass of the electrons in place of a momentum-based object, like a flywheel or like a rotating superfluid or something like that.
Sure. But I guess what I was getting at is that something like, scalar wave or Tesla wave technology might be something wholly different than electricity as we know it. It might be.
Oh, it is. I mean, it's wholly different as than electricity as we know it.
Yeah, and that's what I'm saying is that if this, gravity or if this unknown force-based inertial mass dampening systems use something akin to Tesla or scalar waves, then electricity is just a methodology of converting energy into those systems that are then useful for that purpose.
Electricity is just basically the flow of electrons through some kind of conductor. Correct. Even if that is the vacuum of space, that's still a conductor in which electrons can travel. But what you're talking about is a transmitted or the radiated wave function of the electron motion and of the proton motion in all associated pieces of matter, and that fundamentally is, I suppose, different than electricity, because once that wave is created, it is unto itself a new form of momentum, and it's not tied to the particle anymore. So anything that you do to that wave or interact with that wave does not affect the particle that created it. And so, it is different than electricity in that sense.
Well, I mean, for example, this is all perspective, because fundamentally it can be argued that everything in the universe could be argued to be electric in nature. So you could even perceive internal combustion engines to be electrical in nature, because think about it, your piston comes up, it compresses the fuel in the air, it detonates the fuel, or at least in my design, it detonates the fuel, which propagates, and then it converts all those gases into plasma. And plasma, as we know, is an electrical phenomena. Fire is a form of plasma, and this chemical reaction, all these different subatomic particles interacting with each other, release a lot of energy in the form of electrical potential, and then that electrical potential is used just like an induction heater, but not
right to heat the plasma cloud.
Well, to heat the plasma cloud and heat the air and then expand the piston. So you could argue that an internal combustion engine is just an electric motor powered by hydrocarbons.
Yeah, everything down to it is somewhat electrical in nature, and that's certainly true across the board. There's always an electric component, but I also agree with you in the sense that there's more going on than just the electric component. That other factors significantly play their role in what's possible.
Well, and there might be forms of electricity that we're either wholly unaware of or have barely tapped into. A lot of Tesla's monopolar, single wire transmission systems, people want to go instantly to no wire transmission. It's like, hey, before we jump into no wire transmission, he was also working on single wire transmission. Let's kind of look into that, because there was some work done by, I forget his name. Anyway, there was a lot of work done, and I have their videos of their live experiments. Very fascinating stuff.
Give me some information, because it sounds like something I'd like to look up. Try to remember. No, I've done quite a bit of work with Tesla one-wire technology, and I built several transceivers that way, and I was able to transmit 100 watts down a wire, a single wire, a few hundred feet long. So that was particularly easy, and that one-wire technology has huge potential, but it does operate at quite a high frequency.
Peter Lindemann. That was the guy's name.
Yeah, you're
Peter
talking about
Lindemann.
Peter Lindemann with Borderland Sciences and Eric Dollard, who in conjunction produced a series of amazing videos, which I've mentioned before on the show that people should absolutely watch. Pretty much all of the videos with Eric Dollard and Lindemann in them from Borderland Sciences should be on their watch list. And you will learn a lot about Tesla tech. And it's real Tesla tech, too. It's not,
real deal.
Like Tesla coil stuff.
Yeah, when Peter Lindemann and Eric Dollard were probably some of the first generation of people to truly rediscover a lot of the technology that Tesla was working on. And their primary sources that they worked off of were the patents that Tesla filed. What more reliable source is there than that? And they're like, oh, how do we discover the secrets of Tesla technology? And then Peter Lindemann comes up and goes, I have an idea. Let's read his patents. How novel.
And it's crazy how much is revealed in the patents, but it's kind of a cryptic language, and that can be a little bit confusing at first. I remember reading Tesla's patents as a little kid and having absolutely no idea what the heck he was talking about. And then again, reading them as an adult and completely understanding every word. So it's a whole different world if you don't know the terms, and it takes a long time to acquire the understanding of the weird language used. But if you can understand the concepts, then it's all right there.
Well, the reason why it's so foreign to most people in terms of the linguistics and vernacularities of Tesla's patents is because all patents are like that. Because when you file a patent, you basically want to be as broad as possible, so you don't want to give any specific details or any more than you have to, so that your protection has the widest scope possible. And of course, when you're dealing with bleeding edge electrical phenomena technology, it gets to so broad to the point where you can't really discern a lot of useful information out of it sometimes.
Yeah, Tesla's fun little trick there was to publish the patent and then go do public lectures on it so he could explain to people what was going on there. But there is a lot of stuff missing from the patent, and some of them just don't contain everything that you need to know in order to replicate the device that's patented.
Yep.
Yeah, I've been introduced to Eric Dollar's work by a couple other people too, and they say a lot of the same stuff. There's also a guy did a lot of experiments on YouTube called the Old Scientist.
Oh man, that guy has done some pretty good experiments. The only trouble is that he's sort of converted his channel now so that the really good videos are now paid for, so, unfortunately.
Yeah.
But I mean, the guy's got to be able to fund his project somehow. I mean, it's a place that none of us really want to have to go, is charging people for content. But unfortunately, in his case, in order to pay for the experiments, he had to do that.
I'd love to get a hold of this guy and get him to come on the show or for an interview, or to get a hold of our team.
He'd be a great interview, but he's the kind of guy, and I can tell just by watching his videos, that you'd want to give him a heads up on the subject matter, and he'd probably research it.
So I just want to say real quick, because we don't want to have to charge just for information, because that's not good.
Right, exactly. We're not doing that.
Well, I understand that, right? So, I mean, this is just my thing, looking at this from a more entrepreneurial mindset that, I have, is that what we should do is and this is just me, and, I'm doing this right now, so I'm practicing what I'm preaching, is we should focus on low-hanging fruit technology, commercialize that, and start making money from it so that we can become self-funded and, self-profiting, and then we can take the proceeds from those profits and dump that into our experiments, and then we have basically a positive feedback loop and a cascading build-up effect, if that makes any sense. And then we'll basically have
it's a solid plan. The only trouble is we need somebody to bring products and ideas to market. So I have several things that I've been working on for a long time, and they've gone through multiple revisions. Like right now I'm on Rev 3 of the Universal flyback driver. I've got multiple revisions of the solder here. I'm up to MK6, and that's a portable battery-powered solder. And so I've got a lot of stuff that could be products. The trouble is I have no way to really bring that stuff to market, and that's not my expertise. So if there was somebody that was an expert in that, would be willing to work towards it to share the profits, but didn't require to be paid right away, then it's something that we could work together on. The trouble is I don't have the funding to pay a professional to get me there, and I don't have the skill set right now to get myself there.
If you have designs, I mean, I have some
I have
light
working
manufacturing.
prototypes. I just got to convert them to something that can be commercially viable.
I mean, if you want, we can talk about this later after the podcast. But I do have some manufacturing capabilities, to say the least. At least, for my age and demographic, and current class and situation I find myself in. So, but if you want, we can go ahead and discuss that later, because I might actually be able to give you some light production runs.
Yeah, it depends what your capabilities are. I don't have CNC set up right now, so that's a problem.
I don't have CNCs, but I have manual machines.
The guy that I just added to the WhatsApp group actually is working on a CNC machine right now.
As in he's building one?
What kind of CNC machine do you need? A CNC lathe, a CNC mill, a CNC plasma cutter? Like, what do you mean by CNC?
CNC lathe and CNC mill.
Okay, that's expensive.
Yes, it is, and it needs to be full axes on both.
If you want, what I can do is I'm working on, I've mentioned this before, I'm working on obtaining a $2.5 million Department of Energy grant. Hopefully I'm going to get it. I'm working really hard to get it. What I could do is, one of the requirements is that I need a 20% of the funding of the project to come from tertiary non-federal funding sources. And what I'm going to use the money to buy a lot of CNC lathes, mills, plasma cutters, a whole 9 yards. And what I would do is, if you're willing to give me a backing, what I'll do is I'll basically be like, we can negotiate either infinite usage of the CNC lathes and mills for forever. We can negotiate however many hundreds of universal flyback drivers you want, just produced, here you go, free and clear, there's your payback. I mean, there's a lot of possibilities we could work out for a symbiotic relationship that benefits both of us via conversion.
Yeah, that'd be really cool. Right now, my issue is that I have no upfront capital, so that's obviously a big barrier to getting something done.
Mm-hmm.
Yeah. Well, the DOE is not particularly picky with how these letters of commitment take form. It can come in the form not just of direct funding, which is what you talk about. It can come in the form of used equipment and machinery. It can come in the form of in-kind volunteer hours. It could come in a lot of forms. And honestly, if you just write a letter of commitment for, X amount of dollars, you'd have to trust me on this, but I'm not going to enforce it. I just need the letter of commitment to show to the DOE, and I could basically do what I need to do.
Well, what you could use is the actual hours that I am putting in for real, doing the research here at my lab, and if it doesn't matter the location, and you can just, count it as part of the hours and funding, then yeah, you could count that, because I really am doing that stuff.
Well, the location doesn't matter, but the thing is, it's not like this grant money is free and clear. This grant money is for a very, 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 very specific project, and anything that falls outside of the scope of that project does not count.
So what specifically is the qualification of the project?
It's very low-hanging fruit. It's essentially a wood chip-powered thermoelectric generator unit. Yeah, it's for their biomass energy division. It's by the U.S. Department of Energy, the EERE, which is the Energy Efficiency and Renewables, whatever. I forget what EERE stands for, but yeah.
Very interesting stuff. And again, we just hit the 3-hour mark here on the podcast, and we're getting kind of off topic from the Wolfram stuff, which was like the focus of this live stream to begin with. So
I'm sorry.
No, that's fine. No, this is all super interesting stuff, because it's the next step that needs to be taken. Regardless, it's a step that needs to be taken simultaneous, because this Wolfram thing could just be it could open up. I mean, it's going to open up a lot of stuff, but it might take 10 or 15, maybe even 50 years of working through this to really to figure it out and to come up with something. Meanwhile, there's lots of experiments and lots of technology that's available right now with models that stuff that we have that we can be building and doing. So this is also important. It's just a a little bit it's a little bit different from the fractal stuff, and if people we're coming on here to learn about that Wolfram stuff, and trying to skip ahead, they're going to be like, oh, what's this, and then what are they talking about, you know what I mean?
Yeah,
So,
sorry to get so off topic.
no, it's all right. I like talking about all this stuff. This is the stuff we talk about on this channel and stuff. It's just getting to be 3 hours into this video.
Yeah, it's probably time to call it.
I'm gonna call the stream, but I'm gonna record we're gonna keep this kind of conversation going a little bit, and I'll record what we talk about here after the stream, just in case we do mention some important stuff. I can throw it together in a separate video. So thank you all online who are watching the live stream, and please email me if you have CNC machining and other stuff for parts. I know there was one guy that contacted me, said he had some of that stuff a while ago, and I have more people in the Hover Brothers emails I'm gonna get more people basically together to discuss some of this stuff, and a more collaborative group going. So email me thealienscientist@gmail.com, and get at me about some projects and what you have to offer. We're trying to get a collaboration going of as many many different minds and abilities and skills sets as possible to add to this collaboration. So anyone that wants to get involved, reach out, and let's link up and see what we can pull together here in 2020. Some serious disclosure and some serious awakening going on.
Heck yeah.
Heck
Been a
yeah.
good show.
Yeah, thanks
Year
guys.
2020, year of disclosure.
That's it.
It happened.
All right, thanks for watching, guys, and we're gonna take this up on the flip side. So.